The night sky unfolds above us, a canvas of twinkling lights against the endless dark. Each point of light, a distant sun, burning bright in the cosmic night. Some have burned for billions of years, others are newly born, their fierce light just beginning its journey across the void. There are more stars than grains of sand on every shore, more stars than we could count in 1,000 lifetimes. And yet, we will see only a handful. Not because they are not there, but because the universe is vast, time is slow, and light takes too long to arrive. These are the stars we will never see. But their story still reaches us. When you look up at the night sky, what you're seeing is not the universe as it is, but as it was. The light from even our closest stellar neighbor, Proxima Centauri, takes 4 years to reach us. The light from the stars in the constellation Orion has been traveling for hundreds, even thousands of years before entering your eye. And the faint smudge of the Andromeda Galaxy? That light began its journey 2 million years ago, when our ancestors were just learning to use stone tools. The universe is a time capsule, preserving moments long gone. And we, with our brief lives, can only witness the smallest sliver of its story. Consider this. For every star you can see, there are billions more hidden from view. Some lie behind clouds of cosmic dust. Others are so distant their light, though traveling at 186,000 miles per second, hasn't had enough time to reach us since the universe began. And still others are moving away so rapidly that their light will never reach us at all. The universe is not just vast in space, but in time. Stars are born, live their lives, and die, all on timescales we can barely comprehend. Some burn for just a few million years, others for trillions. Our own sun is middle-aged at 4.5 billion years, with another 5 billion to go before it swells into a red giant, engulfing the inner planets. And yet, despite this enormity, we try to understand. We build telescopes that can peer deeper into space and further back in time. We develop theories that help us grasp the ungraspable. We send out probes, tiny messengers carrying our greetings to the stars. But there will always be more that we cannot see, cannot know, cannot reach. Beyond the edge of our vision, beyond the limits of our instruments, beyond even the boundaries of the observable universe itself, stars burn in silent splendor. Galaxies spiral, planets form. Life perhaps emerges and wonders at its own night sky. This is not a story of limitations, though. It's a story of wonder, because in acknowledging what lies beyond our reach, we gain a deeper appreciation for what we can see and know. The stars visible to us are no less magnificent for being a small sample of the whole. The universe we can observe is no less worthy of study for being a fraction of what exists. As we embark on this cosmic journey together, we'll discover the many reasons why some stars remain forever hidden from us. We'll explore the boundaries of our cosmic horizon, where light itself surrenders to the overwhelming expansion of space. We'll contemplate stars that died long before Earth formed, their light still traveling silently through the void. And we'll consider stars not yet born, whose first light will shine long after our sun has faded to a dim ember. In the tapestry of night, each visible star is surrounded by countless others we cannot see. They form a hidden backdrop, the unseen foundation upon which our visible universe rests. Like the dark matter that outweighs all visible matter, these unseen stars remind us that what we perceive is merely a fraction of what exists. Imagine standing on a shore at night, watching distant ships pass along the horizon. Their lights blink in the darkness, revealing their presence but little more. You might wonder about the people aboard, their destinations, their stories. The stars are like those distant lights, offering tantalizing glimpses of worlds we can never fully know. Yet there is profound beauty in this limitation. There is wonder in knowing that the universe extends far beyond what our eyes can see, our instruments can measure, or our minds can fully comprehend. There is comfort in the knowledge that even as our brief lives flicker and fade, the stars continue their ancient dance, witnessed or not. Tonight, When you look up at the sky, remember that what you see is just the beginning. For every star that catches your eye, billions more remain hidden. They burn in the depths of space, their light traveling through the darkness, perhaps never to be seen by any living thing. And yet, they matter. They shape the universe through their gravity. They forge the elements that will one day form new stars, new planets, perhaps even new life. The stars we will never see are not truly lost to us. Their influence shapes our cosmic home. Their existence enriches our understanding of the universe. And the simple knowledge that they are there, shining in the darkness beyond our sight, adds depth and mystery to our view of the cosmos. So as we settle in beneath this vault of stars, let us marvel at what we can see. Let us wonder at what we cannot. And let us begin our journey through the unseen cosmos, where billions upon billions of stars burn bright, whether we are there to witness them or not. In the silence between heartbeats, in the pause between breaths, listen. Can you hear them? The stars we will never see, calling across the void. Not with sound, for sound cannot travel through the emptiness of space, but with light, with gravity, with the subtle influence they exert on everything around them. They speak a language older than words, telling stories longer than memory. Stories of cosmic birth and death, of elements forged in stellar furnaces, of light traveling across unimaginable distances, only to fade into the expanding darkness. These are the stars we will never see, and this is their story. The night sky appears limitless, an endless expanse, dotted with countless stars. But there is a boundary to what we can see, not because space ends, but because our ability to receive information from it does. This boundary defines what astronomers call the observable universe. The observable universe is everything we can potentially see, everything from which light has had time to reach us since the beginning of time. It's not the entire universe. It's the universe as visible from our particular vantage point, from our place in space and time. Think of it as a cosmic bubble centered on Earth, extending outward in all directions for approximately 46 billion light-years. That number might seem strange. After all, the universe is only about 13.8 billion years old. How can we see things that are 46 billion light-years away if light has only had 13.8 billion years to travel? The answer lies in the nature of space itself. The universe isn't just filled with galaxies flying away from each other through static space. Space itself is expanding, stretching like the surface of an inflating balloon. This means that distant galaxies aren't just moving through space. They're being carried away as the space between us and them expands. When light left the most distant galaxies we can observe, they were much closer to us than they are now. As that light traveled toward us, the space it was moving through continued to expand, stretching the distance. By the time the light reaches us, the galaxies that emitted it have been carried much farther away by the expanding universe. This expansion of space creates the difference between the age of the universe and the current distance to the edge of the observable universe. The light has been traveling for 13.8 billion years, but the objects that emitted that light are now 46 billion light-years away, due to the continued expansion of space during the light's journey. The observable universe is incredibly vast. It contains approximately 2 trillion galaxies, each containing billions or trillions of stars. The total number of stars in the observable universe is estimated to be around 1 septillion. That's a 1 followed by 24 zeros. It's more stars than there are grains of sand on all the beaches on Earth. Yet for all its immensity, the observable universe is still just a fraction of what exists. Beyond our cosmic horizon lie more galaxies, more stars, more planets that we will never see, because their light, racing toward us at 186,000 miles per second, hasn't had time to reach us in the 13.8 billion years since the universe began. And some never will. This is where the story of the stars we will never see truly begins. The expansion of the universe is accelerating. Distant galaxies aren't just moving away from us. They're moving away faster and faster as time goes on. This acceleration is driven by a mysterious force astronomers call dark energy. We don't know what dark energy is, but we can measure its effects. It's pushing the universe apart, stretching space itself at an ever-increasing rate. This acceleration means that some galaxies are moving away from us faster than the speed of light, not because they're breaking any cosmic speed limits themselves, but because the space between us and them is expanding so rapidly that the effective separation speed exceeds light speed. Light from these galaxies, even though it travels at the maximum possible speed allowed by physics, will never reach us. The space it must cross is expanding too quickly. It's like trying to swim against a current that's flowing faster than you can swim. No matter how long you keep at it, you'll never make progress. You'll drift further and further from your starting point. This creates a cosmic horizon, a boundary beyond which we can never see, not because our instruments aren't powerful enough, but because the light from objects beyond that boundary can never reach us. It's a fundamental limit imposed by the physics of our expanding universe. And here's the truly mind-bending part. This horizon is shrinking. As the expansion of the universe accelerates, galaxies that are currently within our observable universe will eventually cross beyond it. Their light, which now reaches us, will one day no longer be able to make the journey. Imagine watching a ship sail over the horizon. At first, you can see the entire vessel, then just the sails. Finally, nothing at all. Similarly, as distant galaxies are carried away by the expanding universe, we'll receive less and less of their light until they fade from view entirely. In the far future, trillions of years from now, if there are still astronomers on Earth or its successor worlds, they will see a very different night sky. Most of the galaxies currently visible will have disappeared from view, carried beyond the cosmic horizon by the relentless expansion of space. The observable universe will have contracted, not because the universe itself has shrunk, but because less of it remains visible to us. The only galaxies still visible will be those in our local group, bound together by gravity strong enough to overcome the expansion. Our Milky Way, Andromeda, and a few dozen smaller galaxies will have merged into a single island universe, floating alone in an apparently empty cosmos. Those future astronomers, unless they have preserved our astronomical records, might never know about the trillions of galaxies that once filled their telescopes. They might conclude that the universe consists only of their single galaxy, unaware of the vast cosmic ocean that lies forever beyond their sight. This fate, this gradual disappearance of the distant universe, is not just a far future possibility. It's happening now. With each passing second, more of the universe slips beyond our cosmic horizon, becoming part of the realm of things we will never see. But the observable universe isn't just limited by the expansion of space. It's also limited by time. The universe had a beginning. Before the Big Bang, approximately 13.8 billion years ago, the universe as we know it did not exist. There was no space, no time, no light to carry information. This means that the oldest light we can possibly see is that which has been traveling since the universe became transparent, about 380,000 years after the Big Bang. Before that time, the universe was an opaque fog of hot plasma, impenetrable to light. That oldest light is what we call the cosmic microwave background radiation. It's a faint glow that permeates all of space, the cooled remnant of the hot, early universe. When we detect this radiation, we're seeing the universe as it was in its infancy, long before stars or galaxies formed. But we cannot see beyond that point. The beginning of the universe is hidden from us, not just because we lack the technology, but because the physics of the early universe prevented light from traveling freely. It's another fundamental limit to our cosmic vision. So the observable universe is bounded by two horizons. One created by the finite age of the universe, which limits how far back in time we can see, and another created by the accelerating expansion of space, which limits what we will ever be able to see in the future. Between these horizons lies everything we can potentially observe. 2 trillion galaxies, 1 septillion stars, countless planets and moons and asteroids and comets. It's an unimaginably vast realm, and yet it's still just a portion of what exists. What lies beyond? We can never know through direct observation. We can theorize, we can infer, We can extrapolate from what we can see to what we cannot. But we will never receive light, radio waves, or any other form of electromagnetic radiation from beyond these horizons. Some theories suggest that the universe is infinite, extending forever in all directions. If so, then the observable universe, as vast as it is, represents an infinitesimal fraction of the whole. An infinite universe would contain infinite stars, infinite galaxies, perhaps even infinite copies of Earth, and everyone on it, given enough space for probability to work its magic. Other theories propose a finite but unbounded universe, like the surface of a four-dimensional hypersphere. In such a universe, if you could travel far enough in one direction, you would eventually return to your starting point, having circumnavigated the cosmos. Still others suggest a multiverse, where our universe is just one bubble in a vast foam of universes, each with potentially different laws of physics, different constants, different possibilities. We may never know which, if any, of these theories is correct. The cosmos beyond our observable universe remains forever hidden from direct view, a realm of possibility and speculation, rather than observation. This is both humbling and awe-inspiring. It reminds us that for all our technological achievements, for all our scientific understanding, there are limits to what we can know. The universe is not just stranger than we imagine, but stranger than we can imagine, because parts of it lie forever beyond the reach of our instruments and our mathematics. And yet, we continue to look. We build more powerful telescopes. We develop more sophisticated theories. We push against the boundaries of the observable universe, trying to glimpse just a little more of the cosmic story. Each new discovery, each distant galaxy or primordial radiation pattern, adds another piece to our understanding of the cosmos. We may never see the complete picture, but we can see enough to marvel at its complexity and beauty. The stars we will never see, those that lie beyond our cosmic horizon, are a reminder of the vastness of existence and the limitations of our perspective. They burn unseen, their light traveling through the void, perhaps to be observed by other eyes in other parts of the universe, or perhaps to travel forever without ever being seen at all. In a way, they are like the parts of our own lives that remain unknown to others. Each of us contains thoughts, memories, and experiences that will never be fully shared or understood by anyone else. We are, each of us, partly visible and partly hidden, like the stars themselves. And just as we find meaning in our connections with others, despite the inevitable gaps in understanding, we find meaning in our connection to the cosmos, despite the limitations of what we can observe. The stars we can see give us insight into those we cannot. The physics that governs nearby galaxies presumably governs those beyond our horizon as well. The observable universe, as vast as it is, serves as our cosmic laboratory. By studying what we can see, we infer what might lie beyond. By understanding the rules that govern the stars within our horizon, we glimpse the possibilities for those that lie forever beyond our sight. In the next chapter, we'll explore another aspect of the stars we will never see. Those whose light, though traveling toward us, has not yet had time to reach Earth. They shine in the darkness, their message on its way, but for now, they remain invisible to our eyes, their stories untold. In the vast silence of space, light moves with unmatched grace and persistence. It travels at the greatest speed possible in our universe, a cosmic constant that shapes everything we see and much of what we cannot. This speed, precisely 299,792,458 meters per second in vacuum, represents both our window to the stars and the reason many will forever remain hidden from us. Light is fast beyond human intuition. In just 1 second, it travels far enough to circle our planet Earth 7.5 times. It races from the moon to our eyes in just over 1 second, creating the slight delay between seeing a lunar astronaut move and hearing their voice over the radio. Light from our Sunday crosses 93 million miles of empty space to reach us in 8 minutes and 20 seconds, bringing warmth, energy, and the visible spectrum that evolved our eyes to see. Yet for all its incredible speed, light still takes time to travel. And in the vast theater of the cosmos, time creates distance that even light cannot fully bridge. Consider our nearest stellar neighbor, Proxima Centauri, a small red dwarf star orbiting in the Alpha Centauri system. The light from this humble star takes 4.2 years to reach Earth. When you observe Proxima Centauri tonight, you're seeing it as it was 4 years ago. If by some cosmic chance it exploded yesterday, we would continue seeing its peaceful glow for 4 more years before witnessing its dramatic transformation. This delay between an event occurring and our observation of it grows with distance. The bright star Sirius, the dog star, appears to us as it was 8.6 years ago. The beautiful Pleiades cluster, the Seven Sisters, shines with light that left those stars about 400 years in the past. The center of our own Milky Way galaxy appears to us as it was 27,000 years ago, when our ancestors were painting on cave walls and mammoths still roamed the Earth. Look deeper, and the delay becomes profound. The Andromeda Galaxy, visible as a faint smudge to the naked eye on dark nights, appears to us as it was 2.5 million years in the past. We see Andromeda not as it is today, but as it was when our earliest human ancestors were just learning to make stone tools, long before modern humans existed. The most distant galaxies visible to our most powerful telescopes appear as they were more than 13 billion years ago, when the universe was young and stars were just beginning to form. Their light has been traveling through the emptiness of space for nearly the entire history of our universe, before finally reaching our instruments. This is the first reason why some stars remain forever hidden from us. Light simply hasn't had enough time to reach us since the beginning of the universe. Imagine a star that formed 12 billion light-years away from our location, but only 3 billion years ago. Its light has been traveling toward us for 3 billion years, covering 3 billion light-years of distance, but it still has 9 billion light-years to go. Given enough time, perhaps another 9 billion years, its light will finally reach Earth. But for now, that star remains invisible to us, not because it doesn't exist, but because its light is still on its way. The universe is filled with such stars, shining brightly but temporarily invisible from our particular vantage point in space and time. They are like messages in cosmic bottles, drifting across an ocean of space, destined perhaps to reach distant shores, but not yet arrived. The most striking examples are stars being born right now in distant galaxies. Throughout the cosmos, clouds of gas and dust are collapsing under their own gravity, heating up until nuclear fusion ignites at their cores, birthing new stars. These stellar newborns immediately begin to shine, their light starting its long journey across the void. But if these stellar nurseries are billions of light-years away, then those fresh beams of starlight will not reach Earth for billions of years. By the time their first light finally arrives at our telescopes, our Sunday may have already swelled into a red giant, engulfing the inner planets. Earth itself might no longer exist as we know it. Humans, if they survive at all, may have evolved into different forms or spread to different worlds. Those future observers, whoever and whatever they might be, will finally witness the light from stars born in our time. They will see them not as aged stars, but as they were at birth, their light preserved by the vacuum of space, like ancient insects in amber, unchanged, despite the billions of years of travel. And just as we cannot yet see stars recently born in distant galaxies, observers in those galaxies cannot see our recently formed stars, or indeed our Sunday as it currently exists. To them, if they have telescopes powerful enough to see our region of space at all, our corner of the Milky Way appears as it was billions of years ago, before our Sunday had even formed from its own cloud of gas and dust. This creates a profound asymmetry in our understanding of the universe. We can see the past of distant regions of space, but not their present. They can see our past, but not our present. We are all, in a sense, temporally isolated from one another, connected only by light that carries outdated information. It's like a cosmic telephone system with billions of years of delay. By the time you receive a call, the person who made it might be long gone. By the time they receive your reply, you too might have vanished. This limitation is not technological but fundamental. No advance in telescope design, no future discovery in physics as we understand it will allow us to see distant stars as they are right now, in this moment. The barrier is not one of engineering, but of the nature of reality itself. The speed of light is not just fast. It is, as far as we can determine, the universal speed limit. Nothing with mass can reach, let alone exceed, the speed of light. No information, no influence, no signal of any kind can travel faster. Einstein's theory of special relativity, now confirmed by countless experiments and observations, establishes this limit as a fundamental feature of our universe. As objects with mass accelerate closer to the speed of light, they require exponentially more energy to gain additional speed. To reach exactly light speed would require infinite energy, an impossibility in our finite universe. When we look up at the night sky, what exactly are we seeing? Each point of light tells a story, not just of what is, but of what was. To understand the stars we will never see, we must first understand how we see the stars at all. Light is our messenger from the cosmos. Every photon that enters your eye has traveled a great distance to reach you. That faint twinkle from a distant star began its journey long ago, traversing the vast emptiness of space, passing through clouds of interstellar dust, navigating around planets and moons, all to arrive at this precise moment, to this precise place, to meet your gaze. The light from our sun takes 8 minutes and 20 seconds to reach Earth. When you feel the warmth of sunlight on your skin, you're feeling the sun as it was 8 minutes ago. If the sun were to vanish this very moment, we wouldn't know it for those same 8 minutes and 20 seconds. We would continue to see its light, feel its warmth, unaware that the source was already gone. This delay becomes more profound the further we look. The light from the nearest star system to our own, Alpha Centauri, takes 4.3 years to reach us. When astronomers observe Alpha Centauri today, they're seeing it as it was 4 years ago. If someone on a planet orbiting Alpha Centauri were looking back at us, they would be seeing Earth as it was 4 years in the past. This concept is what astronomers call look-back time. The further away an object is, the longer its light takes to reach us, and the further back in time we're seeing it. The bright star Sirius? We see it as it was 8.6 years ago. The Pleiades star cluster shines as it was about 400 years in the past. The center of our Milky Way galaxy appears to us as it was 27,000 years ago. Imagine an alien astronomer 1,000 light years away, pointing their telescope at Earth right now. What would they see? Not our modern world of cities and technology, but Earth, as it was in the 11th century. They would see a world without electricity, without airplanes, without the internet or modern medicine. They would see castles and kingdoms, forests where cities now stand. This is the first reason we will never see some stars as they truly are now. By the time their light reaches us, they have already changed. A star that appears stable and bright to us may have already gone supernova, exploding in a brilliant flash. We just haven't received that news yet. The universe operates on a delay, and the further we look, the longer that delay becomes. Our eyes, remarkable as they are, can only detect a tiny fraction of the light that reaches Earth. They evolved to see the kinds of light most useful for our survival on this planet. But stars emit many forms of light invisible to the human eye. Some shine brightly in ultraviolet, others in infrared, and still others in radio waves or X-rays. This is why telescopes have revolutionized our view of the cosmos. They are not just magnifying glasses for the stars. They are time machines and light collectors, gathering faint signals from the distant past and translating invisible forms of light into images we can comprehend. The Hubble Space Telescope, orbiting above Earth's atmosphere, has peered deep into space, capturing light from galaxies so distant that we see them, as they were billions of years ago, not long after the birth of the universe itself. The James Webb Space Telescope sees primarily in infrared light, allowing it to detect stars and galaxies hidden behind clouds of cosmic dust. Radio telescopes capture the whispers of stars and galaxies in wavelengths thousands of times longer than what our eyes can see. Each telescope reveals a different aspect of the cosmic story. Together, they give us a more complete picture of a universe that is vastly more complex and varied than what our eyes alone can perceive. But even with our most powerful telescopes, we're limited by the fundamental nature of light itself. Light travels at a finite speed. Fast, incredibly fast, but not infinitely so. It races through the vacuum of space at 300,000 kilometers per second, or 186,000 miles per second. At this speed, it could circle Earth 7.5 times in just 1 second. And yet, on the cosmic scale, even this tremendous speed proves too slow. The universe is simply too vast. If you could travel at the speed of light, it would take you 100,000 years to cross just our Milky Way galaxy. To reach the Andromeda Galaxy, our nearest large galactic neighbor, would require 2.5 million years. And to travel to some of the most distant galaxies we can observe would take billions of years. This is why astronomers often use the light year as a unit of measurement. 1 light year is the distance light travels in 1 year, about 9.5 trillion kilometers, or nearly 6 trillion miles. When we say a star is 10 light years away, we mean that its light takes 10 years to reach us, and we're seeing it as it was 10 years ago. The most distant objects we can see are more than 13 billion light years away. Their light began its journey when the universe was young, less than 1 billion years after the Big Bang. We're seeing them not as they are now, but as they were in the universe's infancy. This is what makes telescopes like Hubble and James Webb such remarkable time machines. They don't just let us see distant objects, they let us see the universe at different stages of its history. By looking at galaxies at different distances, astronomers can observe cosmic evolution in action, watching how stars and galaxies formed and changed over billions of years. The light from distant galaxies also carries information about the space it has traveled through. As it passes through clouds of gas and dust, certain wavelengths get absorbed or scattered, creating a kind of cosmic fingerprint that tells us about the composition of the materials it encountered along its journey. Even the darkness between stars speaks volumes. The absence of light from certain directions tells us about cosmic structures too dim to see directly. The shadow of an unseen planet passing in front of a distant star tells us about worlds orbiting other suns. So when we look up at the night sky, we're not just seeing points of light, we're seeing history unfolding. We're seeing the past laid out before us, with the nearest stars showing their most recent chapters and the most distant objects revealing the earliest pages of the cosmic story. This perspective gives us a humbling sense of our place in the universe. We are observers of a cosmic drama that began long before us and will continue long after. The starlight that falls on us tonight has been traveling for years, centuries, millennia, making its way across the void specifically to arrive at this moment, to this place, to enter our eyes or our telescopes and tell us its story. Yet for all we can see, there is far more we cannot. Beyond the reach of our most powerful instruments lie stars and galaxies, whose light has not had time to reach us since the beginning of the universe. Others are moving away so rapidly due to the expansion of space that their light will never reach us at all. Still others are hidden behind veils of dust or drowned out by the brilliance of closer, brighter objects. The visible universe is vast beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars. And yet, it is still finite. It has a horizon, a boundary not in space but in time and in our ability to receive light. Think of it this way. Imagine standing in a vast, dark field on a foggy night. You can see nearby objects clearly, more distant ones as dim shapes, and beyond a certain point, nothing at all. That point is not the edge of the field. It's simply the limit of your vision in those conditions. The field continues beyond what you can see. The universe is like that field, but the fog is time itself and the limitation of light's speed. We know there is more beyond what we can see. We can measure its gravitational effects. We can theorize about its nature, but we cannot observe it directly. Not now. Perhaps not ever. This is a profound thought. The universe we can see, as incomprehensibly vast as it is, represents just a fraction of what exists. For every star whose light has reached us, countless others remain hidden from view, shining in the darkness beyond our cosmic horizon. And yet, we keep looking. With each new telescope, with each technological advancement, we push that horizon a little further. We capture light that has been traveling through space since before Earth existed. We piece together the cosmic puzzle, knowing we may never see the complete picture, but finding wonder in each new fragment we discover. As we continue our journey through the cosmos, remember this: when you look at the stars, you're looking back in time. You're seeing them not as they are, but as they were when their light began its journey to your eyes. The star you see might have changed, might have died, might have given birth to new worlds since that light departed. The universe you observe is a historical record, not a live broadcast. And beyond what you can see lies a cosmic ocean of stars and galaxies, shining in splendid isolation, their light still traveling through the void, perhaps never to be seen by any living thing. These are the stars we will never see, not because they don't exist, but because the universe, in its vastness, has set a limit to our vision that no technology can fully overcome. In our next chapter, we'll explore the concept of the observable universe more deeply and come to understand why, despite all our technological advances, some stars will forever remain beyond our sight. Even if we could somehow accelerate a spacecraft to 99.99% the speed of light, a tremendous feat requiring technologies far beyond our current capabilities, it would still take more than 4 years to reach the nearest star beyond our sunday. To reach the center of our galaxy would take nearly 30,000 years. To reach Andromeda, more than 2 million years. And these are just our cosmic neighbors. The universe extends billions of light years in all directions, filled with stars we will never visit, whose light, in many cases, we will never see. This cosmic speed limit creates a kind of provincial isolation. We are limited not just in where we can go, but in what we can know about the present state of distant regions of space. We are, in a very real sense, trapped in a bubble of space-time, able to look outward and backward in time, but unable to perceive the cosmic now, beyond our immediate vicinity. The stars we will never see include all those whose light has not yet had time to reach us. They burn in the darkness, invisible to our eyes and instruments, their existence known to us only through inference and extrapolation. We know they must be there because the universe appears similar in all directions on large scales, a property astronomers call homogeneity. The sections of the universe we can see contain stars and galaxies distributed in statistically predictable ways. It's reasonable to assume that regions we cannot yet see follow similar patterns. We also know that star formation continues throughout the cosmos. The raw materials for new stars, hydrogen and helium, remain abundant even billions of years after the Big Bang. Gravity continues to draw these materials together, forming the stellar furnaces that light up the darkness. So while we cannot see stars whose light has not yet reached us, we can be confident they exist, burning in their distant isolation, perhaps surrounded by planets with their own unique environments and possibilities. There's something poignant about these invisible stars. They represent the gap between what exists and what we can perceive. They remind us that the universe is not only vaster than we can observe, but also richer and more dynamic than our limited perspective reveals. Consider a star forming right now, at this very moment, in a galaxy 12 billion light-years away. Its birth is a magnificent event, with clouds of gas swirling and compressing, heating until nuclear fusion ignites in a sustained reaction that will burn for billions of years. Perhaps planets are already forming in orbit around it, their molten surfaces gradually cooling, atmospheres developing, the complex chemistry of potential life beginning its first tentative steps. All of this is happening now, in cosmic real time. It is as real as the ground beneath your feet or the air in your lungs. And yet, from our perspective, that star does not yet exist. It will not enter our observable reality until its light finally reaches us, 12 billion years from now. In a sense, the universe has a kind of dual existence. There is the universe as it truly is, in its complete present state, with all its stars and galaxies as they exist right now. And there is the universe as we can observe it, with distant regions appearing to us as they were in the remote past, and some regions not appearing to us at all, because their light has not had time to arrive. This duality creates a strange paradox. The universe we can see is not the universe as it is. The universe as it is, we can never fully see. We are like people in a dark room, illuminated only by delayed flashes of light from distant sources, trying to piece together what the room truly contains. And yet, despite these limitations, astronomy has revealed an incredible amount about our cosmos. By studying the light that does reach us, by understanding the physics of stars and the evolution of galaxies, we can infer much about what lies beyond our direct observation. We know, for instance, that the universe is approximately 13.8 billion years old, that it is expanding at an accelerating rate, that it contains structures at many scales, from planets to superclusters of galaxies. We know the basic life cycle of stars, from birth in clouds of gas and dust, through their main sequence where they fuse hydrogen into helium, to their eventual fate as white dwarfs, neutron stars, or black holes depending on their initial mass. All this knowledge comes from light that has reached us, from stars we can see. And from this foundation, we build our understanding of the stars we cannot see, those whose light is still traveling toward us through the vast cosmic dark. In a way, these not yet visible stars represent the future of astronomy. With each passing year, with each passing century and millennium, the sphere of our observable universe expands slightly as light from more distant regions finally completes its journey to Earth. Future astronomers will see stars and galaxies that remain hidden from us today, their light still en route through the interstellar void. If humanity or its successor intelligence survives for millions or billions of years, the observable universe will continue to expand, revealing more and more of what currently lies beyond our cosmic horizon. The stars whose light has not yet reached us will gradually come into view, one by one, revealing ancient events as if they were new. This creates a strange temporal layering to our understanding of the cosmos. The further we look in distance, the further back we see in time. But as time passes here on Earth, we see further into the history of distant regions. It's as if we're slowly peeling back layers of cosmic history, seeing progressively earlier chapters of increasingly distant regions of space. Yet even with infinite time, we would never see the entire universe as it is in any given moment. By the time light from the most distant regions finally reached us, those regions would have changed beyond recognition. The cosmic movie we're watching will always be out of sync, with different regions appearing to us from different eras of cosmic history. This desynchronization is the price we pay for living in a universe where light, though the fastest thing possible, still takes time to travel across vast distances. It creates a fundamental gap between reality and perception, between what exists and what we can observe. And so, the stars whose light has not yet reached us join the list of those we will never see as they truly are now. They exist beyond our current perception, their present state hidden from us by the very laws of physics that make observation possible at all. As we gaze up at the night sky, we might reflect on these invisible stars, burning in distant isolation, their light racing toward us through the void, message bottles launched across an ocean of space and time. Some of these messages will reach future eyes on future worlds. Others will travel forever through an expanding cosmos, never to be read by any conscious mind. They remind us that the universe is not just what we can see, but also what remains hidden. For every star that graces our telescopes, countless others shine unseen in the great cosmic darkness. In the silent expanse of deep space, a profound drama unfolds. The universe itself is stretching, expanding in all directions like the surface of an inflating balloon. This cosmic expansion, first observed by astronomer Edwin Hubble in the late 1920s, transforms not just the structure of space, but the destiny of light itself. It creates perhaps the most profound category of stars we will never see. Those whose light, though traveling toward us for billions of years, will never arrive. To understand this phenomenon, we must first grasp the true nature of cosmic expansion. When astronomers say the universe is expanding, they don't mean that galaxies are simply flying apart through static space, like shrapnel from an explosion. Something far more fundamental is happening. Space itself is stretching. The very fabric of reality is being pulled apart, carrying galaxies along with it like raisins in rising bread dough. This distinction is crucial. Galaxies aren't just moving through space. Space is expanding between them. And unlike ordinary motion, this expansion has no speed limit. While nothing can move through space faster than light, space itself can expand at any rate. There is no cosmic law that prevents two distant points from moving apart at speeds that effectively exceed the speed of light. Not because either point is breaking the speed limit, but because the road between them is stretching. When Hubble made his groundbreaking observations, he discovered that distant galaxies are moving away from us, and the farther they are, the faster they're receding. This relationship, now known as Hubble's law, is the signature of cosmic expansion. It's not that we're at the center of some explosion pushing everything away from us. An observer in any galaxy would see the same effect. It's space itself that's expanding, carrying galaxies along with it. For nearby galaxies, this recession is relatively slow. The Andromeda Galaxy, our nearest large galactic neighbor at 2.5 million light-years away, is actually moving toward us due to mutual gravitational attraction, bucking the trend of cosmic expansion. But beyond our local group of gravitationally bound galaxies, the expansion of space takes over. Galaxies 10 million light-years away recede at hundreds of kilometers per second. Those 100 million light-years distant move away at thousands of kilometers per second. And here lies the critical threshold. At a certain distance, roughly 16 billion light-years from Earth in our current era, galaxies appear to recede at the speed of light. Beyond this distance, they recede even faster. Their effective velocity, caused not by their own motion, but by the expansion of space between us, exceeds the cosmic speed limit. This creates a profound consequence. Light emitted by stars in these ultra-distant galaxies, though traveling toward us at the maximum possible speed, will never reach Earth. The space it must cross is expanding too quickly. For every light-year the photons travel toward us, the expansion of space adds more than a light-year to their remaining journey. It's like trying to walk up a down escalator that's moving faster than you can climb. No matter how long you walk, you'll never reach the top. This boundary, where the recession velocity equals the speed of light, is what cosmologists call the cosmic event horizon. It marks the edge of our observable universe. Not because our telescopes lack the power to see beyond it, but because light from beyond this horizon can never reach us, regardless of how long we wait. But here's the truly mind-bending part. This horizon is not static. It changes over time as the rate of cosmic expansion changes. And according to our current understanding, based on observations of distant supernovae and the cosmic microwave background radiation, the expansion of the universe is accelerating. This acceleration is one of the great mysteries of modern cosmology. Physicists attribute it to a mysterious force called dark energy, which makes up about 68% of the energy content of the universe. Unlike gravity, which pulls matter together, dark energy pushes space apart, and its influence grows as the universe expands. The acceleration of cosmic expansion has profound implications for the stars we will never see. As the expansion rate increases, the cosmic horizon shrinks. Galaxies that are currently visible will eventually cross beyond this horizon. Stars whose light now reaches our telescopes will fade from view, not because they stop shining, but because expanding space prevents their light from completing its journey to Earth. Imagine a star 20 billion light-years away, whose light is currently reaching our telescopes after a journey that began not long after the Big Bang. As the expansion of the universe accelerates, the space between that star and Earth stretches faster and faster. Eventually, its recession velocity will exceed the speed of light. At that point, new photons emitted by the star will never reach us. The star will fade from our observable universe, crossing beyond our cosmic horizon, like a ship sailing over the edge of the world. This fate awaits not just a few distant objects, but the vast majority of galaxies currently visible to our telescopes. If dark energy continues to dominate cosmic evolution as it does today, then in about 2 trillion years, all galaxies beyond our local group will have disappeared from view. The observable universe will have shrunk dramatically, leaving future astronomers with an emptier sky. By that distant future, our Milky Way will have merged with the Andromeda Galaxy and some smaller neighbors, forming a giant elliptical galaxy sometimes called Milkomeda. This combined galaxy, along with a few dwarf satellites, will appear to be the entire universe to any observers who evolve there without access to our ancient astronomical records. Imagine those future astronomers gazing up at a night sky devoid of distant galaxies, unaware of the cosmic ocean that once filled their telescopes. Unless they preserve knowledge from our era, they might develop a very different cosmology, perhaps concluding that their island universe is all that exists, floating alone in an empty void. The evidence for the Big Bang, for cosmic expansion, for the vast network of galaxies that once filled our vision, will have disappeared beyond their cosmic horizon. This is the ultimate disappearing act, removing not just individual stars from our sight, but entire galaxies, galaxy clusters and superclusters. Trillions of stars, most of the observable universe, will eventually become invisible, their light unable to cross the growing gulf of expanding space. But the story of lost light goes deeper still. Even for stars whose light can still reach us, cosmic expansion alters the nature of that light in profound ways. As photons travel through expanding space, their wavelengths stretch, shifting toward the red end of the spectrum in a process called cosmological redshift. This is not the same as the Doppler effect, which causes similar wavelength shifts for objects moving through space. Cosmological redshift happens because space itself expands while the light is in transit. The photons lose energy not through any interaction with matter or fields, but because the cosmic expansion stretches their wavelengths. For distant galaxies, this redshift is substantial. A galaxy 10 billion light-years away might have its light redshifted by a factor of 5 or more, shifting ultraviolet light into the visible spectrum and visible light into the infrared. The most distant galaxies we can observe have their light redshifted by factors exceeding 10, pushing most of their visible emissions into infrared wavelengths that are invisible to the human eye and must be detected by specialized telescopes like the James Webb. As cosmic expansion accelerates, this redshift becomes more extreme. Light from sources near our cosmic horizon is stretched almost beyond recognition, its energy diluted by the expanding space it traverses. Eventually, photons become so redshifted that they shift beyond even the radio portion of the spectrum. Their wavelengths stretch to macroscopic scales. At this point, they become effectively undetectable. Their energy spread too thin across expanding space. This creates another category of stars we cannot see, those whose light reaches us, but has been redshifted beyond our ability to detect it. Their signals arrive too weak, too stretched, too diluted by their journey through expanding space to register in our instruments. This combination of horizons and redshifts means that the observable universe represents just a fraction of what exists. Beyond our cosmic horizon lie more galaxies, more stars, more planets that we will never see, whose light will never reach us. Within our horizon, but near its edge, are objects whose light is so severely redshifted that we can barely detect them, their true nature obscured by the effects of cosmic expansion. The universe beyond our horizon is not a theoretical construct or a philosophical abstraction. It's real space, filled with real stars and galaxies, as physical and concrete as the ground beneath your feet. We know it exists because the universe appears homogeneous and isotropic on large scales. The distribution of galaxies and the cosmic microwave background radiation show the same statistical patterns in all directions, suggesting that the parts of the universe we cannot see are similar to those we can. In a sense, these invisible regions are like continents, yet undiscovered to ancient sailors. Their existence can be inferred from patterns in ocean currents and migrating birds, but they lie beyond the horizon, unreachable and unseen. Unlike earthly horizons, however, our cosmic horizon cannot be crossed. No voyage, no matter how long or how fast, can carry us beyond it, because the space between here and there expands too quickly. This is a profound limitation, not just on what we can see, but on what we can ever know about the universe. The stars beyond our cosmic horizon are permanently invisible to us. their light unable to complete the journey to our telescopes. We can theorize about them, model their likely properties, infer their existence from the patterns we observe in the visible universe. But we can never observe them directly. And as cosmic expansion accelerates, driven by the mysterious dark energy that permeates space, our cosmic horizon shrinks. The observable universe contracts, not because the universe itself is shrinking, but because less of it remains visible to us. With each passing eon, more stars fade from view, crossing beyond a horizon from which no light can return. This gradual disappearance of the distant universe is already underway. Stars near our current cosmic horizon are already becoming invisible, their light unable to reach us as space expands ever faster. This process will continue, accelerating as dark energy exerts more influence over cosmic evolution, until eventually only our local group of gravitationally bound galaxies remains visible. The light from these vanished galaxies doesn't stop traveling. It continues its journey through the void, crossing ever-expanding space that grows between us and them. But that journey becomes literally endless, the distance to be crossed growing faster than the light can traverse it. Like Zeno's paradox made real, these photons can travel forever and still find themselves no closer to their destination. There's something poignant about this lost light, these messages from distant stars that will never be received. They carry information about worlds we will never know, civilizations we will never contact, phenomena we will never observe. They are the unread letters of the cosmos, dispatches from beyond our horizon that drift eternally through the void, their stories forever untold. In a way, every photon that reaches us from a distant galaxy is a survivor, a messenger that began its journey billions of years ago and managed to cross the expanding gulf of space before the acceleration of cosmic expansion made such journeys impossible. Each ancient photon that strikes our telescopes carries information from a universe that was younger, denser, and more interconnected than it is today. The light from the most distant galaxies we can observe began its journey when the universe was less than 1 billion years old. It has traveled for over 12 billion years, crossing space that has expanded dramatically during its transit. This light represents the afterglow of cosmic dawn, when the first stars and galaxies formed from primordial hydrogen and helium, illuminating the universe after its long dark age. That we can see this light at all is remarkable. Had cosmic expansion accelerated sooner, had dark energy exerted its influence earlier in cosmic history, this light might never have reached us. The most distant objects might have crossed beyond our horizon before their light could complete its journey, leaving us with a much smaller, much younger observable universe. This suggests an unsettling possibility. If the acceleration of cosmic expansion continues to increase, if dark energy grows stronger over time as some models predict, then the observable universe will continue to shrink. Future generations will see less of the cosmos than we do, their cosmic horizon drawing closer, their view of the universe more limited than our own. In the most extreme scenarios, this acceleration might eventually become so rapid that it tears apart galaxies, solar systems, planets, and even atoms in an event cosmologists call the Big Rip. Long before such a catastrophic end, however, the observable universe would have shrunk to a tiny fraction of its current size, with almost all distant galaxies having faded from view. Even if such extreme scenarios don't come to pass, the gradual disappearance of the distant universe seems inevitable given our current understanding of cosmic evolution. The stars we will never see include not just those currently beyond our horizon, but many that are visible today, yet destined to fade from view as cosmic expansion accelerates. This creates a strange responsibility for current and near-future astronomers. Our era, spanning perhaps a few billion years in a universe already 13.8 billion years old, represents a unique window of opportunity. We exist at a time when much of the universe remains visible to us, when light from distant galaxies can still reach our telescopes, when the cosmic horizon extends far enough to show us a representative sample of what exists. Future astronomers, billions or trillions of years from now, may not be so fortunate. Their sky may contain just a single giant galaxy, the merged remnant of the Milky Way and its neighbors, floating alone in an apparently empty cosmos. The evidence for the Big Bang, for cosmic expansion, for the vast web of galaxies that once filled space, will have disappeared beyond their cosmic horizon. Unless we preserve our observations, our data, our understanding of the larger cosmos, that knowledge might be lost. Future scientists might develop very different models of the universe, unaware of the rich cosmic ocean that once surrounded their island galaxy before expanding space carried it beyond view. This gives our astronomical observations a certain urgency. We are witnessing a universe that future generations will never see. We are receiving light from galaxies that will eventually fade from view as cosmic expansion accelerates. We are, in a sense, the cosmic historians, recording the larger universe before much of it disappears from sight. And what we cannot see, what lies beyond our cosmic horizon, remains forever unknown to us. We can infer its existence, model its likely properties, theorize about its structure, but we can never observe it directly. The stars beyond our horizon will never be seen from Earth, their light unable to cross the expanding gulf of space that separates us. This is the fate, not just of distant galaxies, but of the photons they emit. Consider a photon emitted by a star just beyond our cosmic horizon. It travels at the maximum possible speed, covering nearly 300,000 kilometers every second. And yet, the space ahead of it expands faster than it can cross. For every light year it travels toward us, the expansion of space adds more than a light year to its remaining journey. This photon, like Sisyphus forever pushing his boulder uphill, is engaged in a journey without end. It will travel for all eternity, crossing countless light years, and yet it will never reach Earth. It carries information about its source star, encoded in its wavelength, polarization, and timing, information that will never be received, a message in a bottle drifting on an infinite ocean. There's something both troubling and beautiful about these cosmic messages that will never be read. They remind us of the vastness of the universe and the limits of our perception. They suggest that for all we can see and know, there is far more that remains hidden, not by technology limitations that might someday be overcome, but by the fundamental physics of our expanding cosmos. The stars we will never see, those whose light cannot reach us due to cosmic expansion, represent perhaps the most profound category of the unseen. They are separated from us not just by distance, but by the nature of space itself. Their invisibility is not a technological limitation, but a feature of our expanding universe, a consequence of the same cosmic evolution that made our existence possible. In this expanding cosmos, we find ourselves in a strange position. We can see far, but not forever. We can know much, but not everything. We exist in a bubble of visibility surrounded by an unseen ocean of stars and galaxies whose light will never reach us. And as cosmic expansion accelerates, driven by the mysterious dark energy that permeates space, our bubble shrinks, our horizon draws closer, and more of the universe fades from view. Yet we continue to look outward, to build more powerful telescopes, to develop more sophisticated theories. We push against the boundaries of our cosmic horizon, trying to glimpse just a little more before it disappears from sight. In doing so, we honor both what we can see and what we cannot, the visible universe that graces our telescopes and the invisible cosmos that lies forever beyond our reach. When we observe the most distant galaxies, we're seeing light from a time when some population 3 stars might still have existed. But even then, we're likely seeing mostly second-generation stars, formed from gas already enriched with the heavy elements produced by the first stellar generation. The actual population 3 stars largely lived and died before their light could reach the region of space where Earth would eventually form. This means that entire stellar populations, crucial to the evolution of our universe, have come and gone without ever being directly observed. They exist for us primarily in theoretical models and computer simulations, their reality inferred rather than seen. They are, in the most literal sense, stars that died before we were born, before our planet formed, before our Sunday ignited. Even within our own Milky Way galaxy, many stars have completed their life cycles without human observation. A supernova explosively near enough to be visible to the naked eye occurs in our galaxy only every few hundred years. The last one observed was in 1604, before the invention of the telescope. Yet thousands of stars have gone supernova in the Milky Way since then. We don't see them because most are hidden behind clouds of interstellar dust, visible only in wavelengths beyond the visible spectrum. These unseen stellar deaths contribute to the evolution of our galaxy, creating heavy elements, triggering new star formation through their shock waves, and in some cases leaving behind exotic remnants, like neutron stars and black holes. They shape our cosmic environment without ever appearing in our night sky. Perhaps the most profound example of stars we will never see are those in the early universe whose light, though traveling toward us for billions of years, will never arrive. Due to the accelerating expansion of the universe, light from extremely distant regions will never reach Earth, as we explored in the previous chapter. This means that countless stars have lived and died in these regions, completely invisible to us, their entire existence hidden beyond our cosmic horizon. There's something poignant about these invisible stars. These cosmic lives played out far from any observing eye. They formed from collapsing clouds of gas, ignited their nuclear furnaces, shone for millions or billions of years, and eventually perished, all without a single photon of their light reaching Earth. They are the cosmic equivalent of the philosophical question about a tree falling in a forest, with no one to hear it. They existed, they mattered in the cosmic scheme, but they left no direct trace in our observable universe. And yet, indirectly, they shape the cosmos we inhabit. The cumulative effect of all stars, seen and unseen, determines the overall evolution of the universe. They convert primordial hydrogen and helium into heavier elements. They influence the temperature and ionization state of the intergalactic medium. They contribute to the gravitational field that shapes the large-scale structure of the cosmos. The stars that died before we were born, whether recently in cosmic terms or in the unimaginably distant past, are part of the foundation upon which our current universe rests. Their matter continues to exist, transformed and recycled into new stars, planets, and eventually living things. As Carl Sagan famously noted, we are made of star stuff, the atoms in our bodies forged in stellar furnaces that, in many cases, exploded long before Earth formed. This creates a profound connection between us and the stars we will never see. Though their light may never reach our eyes, their material legacy lives on in the chemistry of our cosmos, in the elements that make up new stars and planets, and ultimately, in our own physical bodies. We are, in a very real sense, the children of stars long dead, carrying forward their atomic legacy in new forms. As we look up at the night sky, we might reflect on this dual reality, that many of the stars we see no longer exist as they appear, and many that do exist remain forever hidden from us. The universe we observe is both more and less than what actually fills the cosmos. It's a universe of echoes and shadows, of light from the past and darkness hiding the present. The stars that died before we were born remind us of the ephemeral nature of even the most seemingly permanent cosmic objects. Stars that burn for billions of years are still, on the grandest scales, temporary phenomena. They are born, they live, they die, much as we do, though on time frames beyond human comprehension. In this way, the night sky becomes a meditation on impermanence and continuation. Individual stars die, but starlight continues its journey through space, long after its source has vanished. Matter is recycled from one stellar generation to the next, and the human observers who look up in wonder are themselves composed of atoms from long-dead stars, a cosmic cycle of transformation that binds us to the universe in the most fundamental way. Not all unseen stars are hidden by vast distances or the finite speed of light. Some remain invisible, despite being relatively close, obscured by the cosmic fog that permeates our galaxy and many others. Dense clouds of interstellar dust and gas act as cosmic veils, blocking visible light and hiding entire stellar populations from our direct view. These hidden stars, represent another fascinating category of cosmic objects we cannot see with our naked eyes, or even conventional telescopes, yet whose presence and properties can be detected through more sophisticated means. Interstellar dust consists of tiny solid particles, typically less than a micrometer in size, made primarily of carbon, silicon, oxygen, iron, and other elements forged in stellar furnaces and scattered into space. This cosmic dust is accompanied by vast clouds of gas, primarily hydrogen and helium, with traces of other elements. Together, these materials form the interstellar medium, the matter that fills the apparent emptiness between stars. Though sparse by earthly standards, with densities often less than a few hundred atoms per cubic centimeter, these clouds extend across enormous distances, spanning hundreds or thousands of light years. Their cumulative effect creates significant obstacles to our cosmic vision, especially when looking along the plane of our galaxy, where the concentration of dust and gas is highest. The Milky Way's disk, that beautiful band of light stretching across our night sky, appears mottled and irregular precisely because of this dust. The dark patches within the Milky Way, sometimes called the Great Rift, are not regions devoid of stars, but rather dense clouds of dust blocking the light from stars beyond them. These dust clouds absorb and scatter visible light, creating a phenomenon astronomers call extinction. Extinction affects blue light more than red, causing starlight passing through dust clouds to appear redder than it actually is, much as our Sunday appears red at sunset when its light passes through more of Earth's atmosphere. This effect, called interstellar reddening, distorts our perception of distant stars, making them appear cooler and less luminous than they truly are. In the densest regions of these dust clouds, extinction becomes so severe that visible light is blocked entirely. The central bulge of our Milky Way galaxy, roughly 27,000 light-years from Earth, lies behind such a veil of dust. Despite containing billions of stars, including a supermassive black hole at the galactic center, this region appears as a dark zone when observed with optical telescopes. Yet these obscured regions are far from empty. Behind these cosmic curtains lie some of the most active and fascinating regions of our galaxy. Star-forming regions, where new stellar systems are being born from collapsing clouds of gas and dust, are often hidden within the very material that gives them birth. Massive stars, shining brilliantly but short-lived, may spend their entire existence hidden within these clouds, never visible to optical observers. The heart of our galaxy, blocked from our view in visible light, teems with activity. Stars orbit the central supermassive black hole at tremendous speeds. Massive clusters of stars, among the densest in our galaxy, fill the central parsecs. Clouds of molecular gas swirl and collide, triggering new waves of star formation. All of this activity occurs hidden from our direct view, obscured by the interstellar dust along our line of sight. How then do we know what lies behind these cosmic veils? The answer comes from wavelengths of light beyond the visible spectrum, particularly infrared and radio waves, which can penetrate dust clouds with minimal absorption or scattering. Infrared astronomy has revolutionized our understanding of obscured regions of the cosmos. At infrared wavelengths, the dust that blocks visible light becomes nearly transparent, allowing us to peer into stellar nurseries, galactic centers, and other dust-enshrouded environments. Infrared observations reveal the hidden stars behind dust and gas, lifting the veil on cosmic environments that would otherwise remain invisible. The 2-micron All-Sky Survey, and later the WISE, Wide Field Infrared Survey Explorer mission, mapped the sky in infrared wavelengths, revealing millions of previously unseen objects. Hot, young stars embedded deep within their birth clouds. Cool, old stars too faint to detect invisible light. Even entire galaxies, their visible light blocked by dust within them, or within our own galaxy, appeared in these infrared surveys. Radio astronomy provides another window into these hidden realms. Radio waves pass through interstellar dust with almost no attenuation, allowing us to detect phenomena invisible in other wavelengths. Radio telescopes detect the cold hydrogen gas from which stars form, the complex organic molecules in star-forming regions, and the synchrotron radiation from energetic events near black holes and neutron stars. These alternative windows into the cosmos reveal a universe far richer and more complex than what we can see with our eyes alone. They show us that for every star visible in the night sky, many more remain hidden, their light blocked by the very material from which they formed. Perhaps the most dramatic example of hidden stellar populations lies in the plane of our Milky Way galaxy. When we look toward the constellation Sagittarius, we're looking toward the center of our galaxy, a region that should blaze with the light of billions of stars concentrated in the galactic bulge. Instead, we see a dark rift, where the combined effect of countless dust particles blocks most visible light from reaching us. Infrared observations transform this view entirely. In near-infrared wavelengths, the dust becomes more transparent, revealing a bright concentration of stars. In mid and far infrared, we can see all the way to the galactic center, observing the environment around our central supermassive black hole, Sagittarius A star. The difference between visible and infrared views of the galactic center is striking. What appears as a dark, nearly empty region in visible light is revealed as one of the most densely packed stellar environments in our galaxy when observed in infrared. Millions of stars, invisible to optical telescopes, shine brightly in infrared images, their light finally reaching our detectors after passing through the interstellar dust. Similar revelations occur when we observe star-forming regions throughout our galaxy. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, contains a cluster of young stars still partially embedded in their birth cloud. Optical telescopes reveal some of these stars, but infrared observations show many more, including some still surrounded by the protoplanetary disks from which planetary systems might form. Even more dramatic are the completely obscured star-forming regions, invisible in optical light, but brilliant in infrared. The Rho-Ophiuchi cloud complex, one of the closest star-forming regions to Earth at just 430 light-years distant, appears in visible light as a dark nebula, blocking the light of background stars. In infrared, it reveals dozens of young stellar objects hidden within the dust, some less than 1 million years old, stellar infants by cosmic standards. This hidden star formation occurs throughout our galaxy, particularly along the spiral arms where gas and dust concentrate. Massive molecular clouds like the Taurus molecular cloud, the Perseus molecular cloud, and many others harbor stellar nurseries, hidden from optical view. Within these clouds, gravity draws matter together, forming dense cores that eventually collapse to form new stars. These young stars, still embedded in their birth material, heat the surrounding dust, which then glows in infrared wavelengths. This infrared emission reveals not just the stars themselves, but the environments around them, including circumstellar disks that may evolve into planetary systems. What remains invisible in optical light becomes a dynamic, evolving landscape in infrared and radio wavelengths. The hidden stars behind dust and gas include some of the most massive and luminous stars in our galaxy. These stellar giants, sometimes exceeding 100 times the mass of our Sun, burn hot and bright, but often form in dense molecular clouds that obscure them from optical view. Their intense ultraviolet radiation ionizes the surrounding gas, creating bubble-like structures called HII regions, while their powerful stellar winds sculpt the surrounding material into complex shapes. Despite being hidden from direct view, these massive stars profoundly influence their environments. They compress nearby gas, potentially triggering new generations of star formation. They enrich the interstellar medium with heavy elements through stellar winds, and eventually, supernova explosions. Their energy input helps determine the temperature and ionization state of the interstellar medium across large regions of the galaxy. When these massive stars explode as supernovae, they may remain partially or completely hidden by dust, their optical light absorbed before it can reach us. However, their higher energy emissions, particularly in X-rays and gamma rays, can penetrate the dust, alerting us to these cosmic cataclysms, even when they occur in obscured regions. Beyond our galaxy, dust obscuration becomes even more significant. Spiral galaxies like our own, contain vast amounts of dust concentrated in their disks. When we observe these galaxies edge-on, their dust lanes are clearly visible as dark bands cutting across the galactic disk. These dust lanes hide millions or billions of stars that lie behind them from the perspective of Earth-based observers. Some galaxies contain so much dust that they are virtually invisible in optical wavelengths. These ultraluminous infrared galaxies, ULIRGs, emit most of their energy in infrared wavelengths. Their visible light absorbed by internal dust, heated by intense star formation or active galactic nuclei. Without infrared astronomy, these galaxies and the stars within them would remain largely unknown to us. Even more extreme are the stars and galaxies hidden behind molecular clouds within our own Milky Way. The zone of avoidance, a band around the galactic plane where extragalactic objects are difficult or impossible to detect in visible light due to obscuration by galactic dust, hides roughly 20% of the extragalactic sky from optical telescopes. Millions of galaxies, containing billions of stars, lie behind this dusty veil, invisible until observed in wavelengths that can penetrate the obscuring material. The hidden stars behind dust and gas remind us that our perception of the universe is filtered by the properties of light and the materials it encounters on its journey. What we see with our eyes or optical telescopes represents just a fraction of what exists, a cosmic censoring imposed by the very material from which stars and planets form. Yet this obscuration also creates some of the most beautiful objects in our night sky. The dark nebulae, appearing as starless voids against the rich stellar background, have entranced observers for centuries. The Horsehead Nebula in Orion, the Coal Sack near the Southern Cross, the Pipe Nebula in Ophiuchus's dark clouds, sculpted by stellar winds and gravity, create striking silhouettes against the star-filled background. These dark nebulae, rather than being empty regions, often contain the seeds of future stellar generations. Within their cold, dense interiors, gravity gradually draws material together, eventually leading to the formation of new stars. What appears as an absent-sea dark region, without star soften, contains stellar embryos, future suns as yet unborn, hidden from our direct view but detectable through their effects on the surrounding material. This cycle of obscuration and revelation is fundamental to stellar evolution. Stars form within dense clouds that hide them from view. As they evolve, many stars eventually disperse their surrounding material through radiation pressure and stellar winds, revealing themselves to optical observers. Later generations of stars form from this enriched material, beginning the cycle anew. The hidden becomes visible, and what is visible later contributes to hiding something else. Our technological evolution mirrors this cosmic cycle. Throughout most of human history, we could observe the universe only in visible light, our perception limited to what our eyes could detect. The development of infrared, radio, ultraviolet, X-ray, and gamma-ray astronomy has progressively lifted these veils, revealing cosmic environments and phenomena previously hidden. Each new observational window shows us stars and structures invisible in other wavelengths. Radio telescopes reveal the cold hydrogen from which stars form. Infrared telescopes show us stars still embedded in their birth clouds. Ultraviolet telescopes detect the hot atmospheres of massive stars. X-ray telescopes find the energetic environments around neutron stars and black holes. Together, they provide a multi-wavelength portrait of a universe far richer and more dynamic than any single perspective can capture. This multi-wavelength view is crucial for understanding the hidden stars behind dust and gas. By combining observations across the electromagnetic spectrum, astronomers can determine the properties of obscured stars, map the distribution of dust and gas that hides them, and understand the environments in which they form and evolve. Advanced techniques like spectroscopy, polarimetry, and interferometry further enhance our ability to study obscured regions. Spectroscopy reveals the composition and physical conditions of the obscuring material. Polarimetry measures how dust grains align with magnetic fields, providing insights into the structure of dusty environments. Interferometry combines multiple telescopes to achieve resolution high enough to peer into the hearts of dusty galaxies and star-forming regions. With these tools, astronomers have mapped the distribution of dust throughout our galaxy and beyond. created three-dimensional models of obscured stellar populations and tracked the evolution of stars from their dusty birth environments to their eventual emergence into clearer view. The hidden stars behind dust and gas, once completely invisible to us, have gradually revealed their secrets. Yet many remain hidden, their light blocked by the cosmic fog that permeates our galaxy. In the densest star-forming regions, in the galactic plane, in the centers of galaxies, stars shine unseen by optical observers, their presence known only through their effects on surrounding material or through observations in wavelengths that can penetrate their dusty shrouds. These hidden stars remind us that the universe contains far more than what is immediately apparent. Beyond what we can see with our eyes lies a richer cosmos, populated by stars in every stage of evolution, from birth to death, many obscured from direct view, but nonetheless integral to the cosmic ecosystem. As we continue our journey through the stars we will never see, remember that some of the most fascinating stellar populations lie hidden, not by vast distances or the finite speed of light, but by the very material from which stars form. Behind the cosmic veils of dust and gas, stars are born, live, and die, their light absorbed and scattered, but their influence extending far beyond their obscured environments. Within galaxies, dark matter halos provide the gravitational potential wells in which gas can accumulate and cool. But complex interactions between dark matter and ordinary matter can also disrupt potential star-forming regions, particularly in the turbulent environments of merging galaxies or galaxy clusters. The interplay between gravitational attraction and various opposing forces creates a cosmic filtering process, allowing only a fraction of the universe's gas to form stars. This selective star formation means that for every star that shines, many more potential stars remain unrealized, existing only in the realm of possibility. These stellar might-have-beens represent another dimension of the cosmic story, a shadow population of objects that lack the specific combinations of mass, density, temperature, and isolation necessary to become true stars. They remind us that the universe we observe represents just one manifestation of cosmic possibility, one arrangement of matter and energy among countless alternatives. In quantum physics, theorists sometimes discuss the concept of virtual particle-ephemeral entities that briefly pop into existence due to quantum fluctuations, only to disappear again almost immediately. In a similar vein, we might think of the stars that will never exist as virtual stars, stellar possibilities that approach realization, but never quite achieve the stable configuration necessary for sustained nuclear fusion. These virtual stars exist in a liminal state, neither fully present nor entirely absent from the cosmic narrative. They influence the evolution of galaxies through the gravitational effects of their constituent gas. They participate in the cycling of elements between stars and the interstellar medium. They absorb and emit radiation, affecting the temperature and ionization state of their surroundings. Yet they never cross the threshold into true stardom, never ignite the nuclear fires that would make them visible across cosmic distances. Perhaps the most striking examples are found in colliding galaxies, where enormous quantities of gas are compressed along shock fronts, creating ideal conditions for star formation. Yet much of this gas remains sterile, unable to collapse into stars despite its high density. The turbulent environment, with rapidly changing gravitational forces and intense radiation from newly formed massive stars, disrupts the delicate process of stellar birth, preventing many potential stars from forming. The Antennae galaxies, a pair of colliding spiral galaxies about 65 million light-years from Earth, illustrate this phenomenon. The collision has triggered the formation of thousands of massive star clusters, making the Antennae one of the most active star-forming systems known. Yet astronomers estimate that only about 5% of the available gas will ultimately form stars. The remaining 95% represents thousands of billions of potential stars that will never exist. Similar processes occur in the turbulent environments of galactic centers, where the interplay between gravity, magnetic fields, and radiation creates conditions simultaneously conducive to and disruptive of star formation. The center of our own Milky Way contains the central molecular zone, a region with enough dense gas to form millions of stars. Yet star formation in this region appears suppressed relative to the available material, with much of the gas likely to be dispersed or ejected before it can collapse into stellar objects. In the distant future, as galaxies exhaust their easily accessible gas reserves, star formation will become increasingly rare, despite the continued presence of substantial gas in the galactic halo and intergalactic medium. This gas, too diffuse or too hot to form stars under natural conditions, represents a vast reservoir of stellar potential that will remain forever unrealized. The stars that will never exist include potential stellar populations in environments we're only beginning to understand. Primordial black holes, formed in the early universe, might have disrupted star formation in their vicinity by accreting or ejecting gas that might otherwise have formed stars. Alternative dark matter models suggest ways in which the gravitational influence of dark matter might have prevented the formation of certain stellar populations, particularly in the early universe and in dwarf galaxies. Even our understanding of star formation itself continues to evolve, suggesting additional categories of never-to-exist stars. Recent simulations indicate that the very first generation of stars formed from pristine hydrogen and helium before any metals were present in the universe may have had a different mass distribution than later stellar populations. Many potential low-mass primordial stars may never have formed due to the different cooling properties of metal-free gas, representing another population of stellar might-have-beens. In the most extreme environments, such as the ergosphere of a rotating black hole or the vicinity of a neutron star merger, conditions might briefly exist that could lead to nuclear fusion outside the context of a conventional star. These exotic scenarios represent alternative pathways for the same fundamental processes that power stars, potentially creating short-lived stellar-like phenomena that never develop into stable stars. The stars that will never exist remind us that the universe we observe represents just one manifestation of cosmic possibility. For every star that shines, many more potential stars remain unrealized, their constituent material dispersed through space or incorporated into other cosmic structures. They exist as ghostly possibilities, paths not taken in the branching evolution of our cosmos. Yet these unrealized stars still matter. Their constituent gas contributes to the dynamics of galaxies. Their gravitational influence shapes the distribution of matter on various scales. Their potential energy remains part of the cosmic inventory, available for other processes if not for stellar formation. They represent not absence, but alternative. Not failure, but different manifestation of cosmic creativity. As we contemplate the stars we will never see, these never-to-exist stars offer perhaps the most philosophical category, challenging us to consider not just what is beyond our vision, but what lies beyond reality itself in the realm of cosmic possibility. As we journey through the stars we will never see, we've explored those too distant for their light to have reached us, those hidden by cosmic dust, and those that never came to be. But perhaps the most profound category awaits us still. The stars whose future light will never reach Earth, though they shine brilliantly in distant regions of space. This is a story of cosmic horizons and the accelerating expansion of the universe. It's about light that begins its journey toward us, but never arrives, not because it's blocked or absorbed, but because the very fabric of space stretches too quickly beneath its path. It's about the shrinking observable universe and the cosmic isolation that awaits in the distant future. To understand this phenomenon, we must revisit the expanding universe. As established by Hubble's observations and confirmed by decades of subsequent research, galaxies are moving away from each other because space itself is stretching. This expansion affects not just the distance between galaxies, but the journey of light traveling through this expanding space. When light leaves a distant galaxy, heading in our direction, it must cross space that is itself expanding. The photons travel at their immutable speed of 300,000 kilometers per second. But the space they must cross grows larger with each passing moment. It's like running on a stretching treadmill. Maintaining a constant speed, the destination moves further away. For galaxies relatively close to our Milky Way, this effect is minimal. their light easily overcomes the expanding space and reaches our telescopes. For very distant galaxies, however, the expansion becomes increasingly significant. Beyond a certain threshold, the cosmic event horizon galaxies recede faster than their light can travel toward us. Light emitted by stars in these ultra-distant galaxies, though traveling at the maximum possible speed, will never reach Earth. This horizon isn't static. It changes as the rate of cosmic expansion changes. And according to our current understanding, based on observations of distant supernovae and the cosmic microwave background radiation, the expansion of the universe is accelerating, driven by a mysterious force called dark energy. Dark energy, making up about 68% of the energy content of the universe, causes space to expand at an ever-increasing rate. This acceleration has profound implications for the light traveling through the cosmos. As expansion speeds up, the cosmic horizon shrinks. Galaxies that were once within our observable universe gradually slip beyond, their light no longer able to overcome the expanding gulf between us. The light that has already left these galaxies continues its journey, but new light, the light that would show us these galaxies as they exist now and will exist in the future, will never reach us. We are seeing the final transmissions from these distant regions, the last messages before communication becomes impossible due to cosmic expansion. This process is already underway. Galaxies near our current cosmic horizon are already sending their final signals to Earth. Light emitted from these galaxies today will never reach us, the space between expanding too rapidly for even light to cross. We see these galaxies as they were billions of years ago, and we will never see them as they exist now or will exist in the future. The implications are profound. Of the roughly 2 trillion galaxies currently visible to our telescopes, the vast majority will eventually disappear from view. Their light, unable to overcome the expanding space between us, will never reach future observers on Earth or its successor worlds. The observable universe will gradually contract, not because the universe itself is shrinking, but because less of it remains visible as cosmic expansion accelerates. This contraction of the observable universe unfolds over enormous timescales. In about 2 trillion years roughly, 150 times the current age of the universal galaxies beyond our local group will have disappeared from view. The local group, gravitationally bound and therefore able to overcome cosmic expansion, includes our Milky Way, the Andromeda Galaxy, and about 50 smaller satellite galaxies. This island of visibility in an increasingly invisible cosmos will represent the entire observable universe for any observers who might exist at that distant epoch. By this time, the Milky Way and Andromeda galaxies will have merged into a single giant elliptical galaxy, sometimes called Milkomeda. This combined galaxy, along with its satellite galaxies, will appear to be alone in the universe, floating in what seems to be an empty void. The evidence for the Big Bang, for cosmic expansion, for the vast network of galaxies that once filled our vision, will have disappeared beyond the cosmic horizon. Future astronomers, unless they preserve records from our era, might develop very different models of the cosmos. They might conclude that their island universe is all that exists, having no observational evidence for anything beyond. They might theorize a static, island universe rather than the expanding cosmos we now know, their view limited by the shrinking cosmic horizon. The light that will never reach us includes not just images of galaxies as they currently exist, but chronicles of their future evolution. We will never observe directly how these distant galaxies change over the coming billions and trillions of years. We will never see new stars form in these remote systems, never witness their future supernovae, never observe how they merge and interact with other galaxies in their vicinity. Consider a galaxy currently visible to our telescopes, perhaps 10 billion light-years away. We see it as it was 10 billion years ago, when the universe was relatively young. That galaxy has continued to evolve during the intervening billions of years. New stars have formed, old ones have died, perhaps civilizations have risen and fallen. But this more recent history will never be visible to us. The light carrying these cosmic updates, though traveling toward Earth at the maximum possible speed, will never arrive due to the accelerating expansion of space. This creates a strange asymmetry in our cosmic perspective. We can see these distant galaxies as they were in the past, but their present and future remain forever hidden from us. It's as if we're reading a novel where the later chapters progressively disappear, leaving the story eternally unfinished. For each distant galaxy currently visible to our telescopes, there exists a temporal horizon, a moment in its history, beyond which we will never see. Light emitted before this critical time can still reach Earth, while light emitted after will never arrive. This horizon varies by galaxy, with more distant galaxies having earlier cutoff points in their histories. The most distant galaxies currently visible to our telescopes are seen as they were just a few 100 million years after the Big Bang. Their temporal horizons might be as early as 1 or 2 billion years into cosmic history. We will never observe directly how these galaxies evolved after that early epoch. The cosmic chronicle, from our perspective, remains perpetually incomplete. This phenomenon affects not just our observation of distant galaxies, but all information transfer across cosmic distances. Radio signals, whether natural or artificial, face the same limitations as visible light. Beyond a certain distance, signals cannot cross the expanding gulf of space. This creates a fundamental limit to potential communication or information exchange across the cosmos. If intelligent civilizations exist in distant galaxies, their signal 7, if deliberately aimed at Earth, might never reach us if sent after their galaxy's temporal horizon. Similarly, signals we send today toward very distant galaxies will never arrive if those galaxies now lie beyond our cosmic horizon. The accelerating universe progressively isolates regions of space, preventing even light-speed communication between them. This cosmic isolation becomes more pronounced as time passes. In the far future, trillions of years from now, if intelligence still exists in our galaxy, it will find itself in an increasingly lonely universe. The once vast observable cosmos would have contracted to just the local group of galaxies. The rich tapestry of distant galaxies that fills our current telescopic images will have faded from view, their light unable to reach us through the rapidly expanding space. By 100 trillion years from now, star formation in this island universe will have largely ceased. The massive stars that now illuminate our galaxy will be long gone, with only red dwarfs and stellar remnants remaining. These aging stars will provide the only direct evidence of a wider cosmos, their compositions and motions bearing the imprint of the universe's earlier, more connected state. As the universe continues to age and expand, even these stellar witnesses will gradually disappear. White dwarfs will cool to black dwarfs. Red dwarfs will eventually exhaust their nuclear fuel. Black holes will slowly evaporate through Hawking radiation. The visible universe will fade to darkness, with only the occasional flash of light from rare events, like proton decay, neutron star collisions, or black hole mergers, briefly illuminating the cosmic night. In this far future universe, the evidence for anything beyond the local group will be increasingly indirect and tenuous. Future scientists might infer the existence of a once larger observable universe from subtle clues in particle physics, cosmic ray backgrounds, or the distribution of matter within their island galaxy. But direct observation of the wider cosmos will be impossible. The light from distant regions unable to reach them through the rapidly expanding space. This progressive isolation of cosmic regions creates perhaps the most profound category of stars we will never see. Those whose future light is forever cut off from us by cosmic expansion. Unlike stars too distant for their light to have reached us yet, these stars have no light from any point in their future that will ever reach Earth, regardless of how long we wait. The barrier is not one of distance alone, but of the fundamental nature of our expanding cosmos. Even if we could somehow freeze the universe at its current state, preventing further expansion, the light from beyond our current cosmic horizon would eventually reach us, revealing those distant regions. But in our actual universe, with its accelerating expansion, that light will never arrive. The gulf grows faster than light can cross it. This creates a poignant asymmetry. We can see light from the distant past of these galaxies' light emitted before the critical temporal horizon, but never from their more recent history or future. It's as if we're permitted a glimpse of cosmic childhood, but forever barred from seeing maturity or old age. For galaxies near our current cosmic horizon, the temporal cutoff might be when the universe was just a few billion years old. We see these galaxies in their youth, with vigorous star formation and evolving structures. We will never see how they matured, how their spiral arms developed, how their central black holes grew, how they interacted with neighboring galaxies over the subsequent billions of years. This limitation affects all forms of electromagnetic radiation and, indeed, all information transfer across these cosmic distances. Neutrinos, gravitational waves, any conceivable carrier of information are bound by the same cosmic speed limit, and all face the same expanding gulf of space. No signal sent after the temporal horizon can ever reach us, regardless of its nature or the technology used to detect it. This creates a fundamental boundary to our knowledge of the cosmos. No future telescope, no matter how sensitive, can reveal the current state of galaxies beyond our cosmic horizon. No future technology, no matter how advanced, can bring us real-time images of these distant regions. The barrier is not technological, but inherent in the physics of our expanding universe. The accelerating expansion also affects our ability to explore the cosmos, even theoretically. A spacecraft leaving Earth today could, in principle, eventually reach galaxies currently within our observable universe, but destined to cross beyond our cosmic horizon. But such a craft could never return, nor could it send signals back to Earth once the destination galaxy crossed beyond the horizon. It would be a one-way journey into cosmic isolation. This limitation applies not just to physical travel, but to all forms of interaction or influence. Regions of space currently visible to us will become increasingly disconnected, not just from our observation, but from any causal influence we might exert. The universe fragments into causally disconnected regions that can no longer interact or exchange information. This causal disconnection represents perhaps the most profound aspect of the light that will never reach us. It's not just that we cannot see these distant regions, it's that we cannot interact with them in any way. They become, for all practical purposes, separate universes, their future evolution unfolding in isolation from our region of space. Yet these causally disconnected regions still exist. They continue their cosmic evolution, forming stars, perhaps nurturing life, experiencing the same physical processes that occur in our observable region. Their reality is not diminished by their invisibility to us. They simply exist beyond our cosmic horizon, sending light that stretches eternally through ever-expanding space without ever reaching our telescopes. In a sense, the light that will never reach us represents the ultimate cosmic isolation. It establishes fundamental limits, not just to what we can see, but to what we can ever know about the universe. It creates boundaries to potential communication, exploration, and influence that cannot be overcome, regardless of technological advancement. This cosmic isolation unfolds gradually over trillions of years. It's already begun, with the most distant regions of the observable universe now sending their final signals toward Earth. As cosmic expansion continues to accelerate, more and more of the currently visible universe will slip beyond our cosmic horizon, their light unable to reach future observers. By the time the universe is 100 trillion years old, the observable cosmos will have shrunk dramatically. By 1 quadrillion years, only the local group will remain visible. By 1 quintillion years, even the evidence for the earlier, more connected state of the universe will have faded almost entirely. Future intelligence, if it exists, will inhabit an apparently island universe, with little observational evidence for anything beyond. This progressive isolation creates a strange responsibility for current and near-future astronomers. Our era, spanning perhaps a few billion years in a universe already 13.8 billion years old, represents a unique window of opportunity. We exist at a time when much of the universe remains visible to us, when light from distant galaxies can still reach our telescopes, when the cosmic horizon extends far enough to show us a representative sample of what exists. The observations we make now, the data we collect and preserve, may represent the only direct evidence future cosmic inhabitants will have for the larger universe beyond their shrinking horizon. Without our astronomical records, future scientists might develop very different models of the cosmos, unaware of the vast cosmic ocean that once surrounded their island galaxy. before expanding space carried it beyond view. This gives our astronomical observations a certain urgency and poignancy. We are witnessing a universe that future generations will never see. We are receiving light from galaxies that will eventually fade from view as cosmic expansion accelerates. We are, in a sense, the cosmic historians, recording the larger universe before much of it disappears from sight. The light that will never reach us includes the stories of countless stars, galaxies, and perhaps civilizations that will remain forever untold from our perspective. Their cosmic narratives continue, but the later chapters remain hidden from us. The light carrying those stories unable to complete its journey through ever-expanding space. And yet, knowing these regions exist, even if we cannot see them directly, enriches our understanding of the cosmos. It reminds us that the observable universe represents just a fraction of what exists. That beyond our cosmic horizon lies more space, more galaxies, more possibilities, unfolding in parallel with our own. In this way, the future light that will never reach us represents both a limitation and an expansion of our cosmic perspective. It limits what we can directly observe while reminding us that the universe extends far beyond what we can see, that reality is not confined to the observable. As we contemplate the night sky, we might reflect that for every star we can see, countless others exist whose future light will never reach us. They shine in the darkness beyond our cosmic horizon, their stories continuing, even as their visibility to us gradually fades. They remind us that the universe is not just vaster but more dynamic, more diverse, and more interconnected than our observations alone can reveal. Beyond our cosmic horizon lies a vast expanse that we can never directly observe, an unseen realm that exists beyond the limits of our vision, beyond the reach of our most powerful telescopes, beyond even the theoretical boundaries of what can be known through observation. This is the universe we will never know, regions of space and time that remain forever invisible to us, not through technological limitations that might someday be overcome, but through fundamental physical constraints that cannot be circumvented. This invisible cosmos isn't a theoretical abstraction or a philosophical conjecture. It's real space filled with real stars, galaxies, and perhaps even civilizations, as tangible and concrete as the ground beneath your feet. Yet it remains forever hidden from direct observation, its existence inferred rather than seen, its properties modeled rather than measured. The universe we will never know consists of multiple overlapping categories, each hidden from us for different but related reasons. First, and most fundamental, is what cosmologists call the unobservable universe regions, beyond our cosmic horizon, where light has not had time to reach us since the beginning of the universe. These regions exist beyond the roughly 46 billion light-year radius that defines our observable bubble. Due to the finite age of the universe, approximately 13.8 billion years, and the finite speed of light, roughly 300,000 kilometers per second, there exists an absolute limit to how far we can see. Light from beyond this horizon has simply not had enough time to reach us. No matter how powerful our telescopes become, they cannot detect light that hasn't arrived yet. What's more, as we discussed in previous chapters, the accelerating expansion of the universe ensures that much of this light will never reach us. Regions currently beyond our cosmic horizon will remain forever invisible, sending no information that can ever cross the growing gulf of expanding space. But the unobservable universe extends far beyond just what lies outside our current horizon. Cosmological models suggest that the universe we can observe represents just a tiny fraction of what exists. The total universe may be hundreds or thousands of times larger than the observable portion, or it may be infinite, extending without end in all directions. During the inflationary period, in the first fraction of a second after the Big Bang, the universe expanded exponentially, multiplying its size by a factor of at least 10 raised to the 26th power in less than a trillionth of a second. This rapid expansion stretched microscopic quantum fluctuations into the macroscopic density variations that would eventually form galaxies and larger cosmic structures. But inflation also pushed most of the early universe far beyond what we can ever observe. Regions that were in causal contact before inflation close enough to interact and exchange information were suddenly separated by distances so vast that light from one region could never reach the others, even over the entire future history of the universe. This means that the universe beyond our observable bubble is not just more of the same. It may contain regions with different properties, different structures, perhaps even different physical constants. The variations in density and energy that seeded galaxy formation in our observable universe would have played out differently in regions beyond our horizon, potentially creating cosmic environments very different from what we can observe. Some inflationary models suggest an even more radical possibility: a multiverse composed of countless bubble universes, each with potentially different physical laws. In these models, our observable universe is just one bubble in a vast cosmic foam, with other bubbles forever beyond our observation. These other universes may have different numbers of dimensions, different fundamental forces, different elementary particles, or other variations that would make them profoundly alien compared to our familiar cosmos. Whether or not such exotic possibilities are real, the standard cosmological model firmly establishes that the universe extends far beyond what we can observe. There are more stars, more galaxies, more planets, and more possibilities beyond our cosmic horizon than within it, perhaps infinitely more. And we will never directly observe them, no matter how long we wait or how advanced our technology becomes. This vast unseen cosmos affects our understanding of our place in the universe. The Copernican principle suggests that we do not occupy a special or privileged location in the cosmos, but our observable bubble is, in a sense, uniquely centered on us. Each observer in the universe has their own observable bubble, centered on their location. What lies beyond one observer's horizon may be visible to another positioned elsewhere in the cosmos. This creates a strange relativity to cosmic knowledge. Different observers, depending on their location in space and time, have access to different subsets of the total universe. No single observer can see the entire cosmos. Each perspective is limited, partial, a small window onto a reality too vast to be encompassed by any single viewpoint. The universe we will never know includes not just what lies beyond our current horizon, but also what existed before the universe became transparent to light, approximately 380,000 years after the Big Bang. Before this time, the universe was an opaque plasma, too hot and dense for light to travel freely. The earliest light we can detect is the cosmic microwave background radiation, the cooled remnant of this hot early universe. What happened before this cosmic dawn remains hidden from direct observation. We can infer the conditions of the early universe through theories and models tested against the patterns in the cosmic microwave background and the abundance of light elements created in the first minutes after the Big Bang. But we cannot directly observe the universe during its infancy, when it transformed from a hot, dense state to the cooler, more structured cosmos we see evidence of today. This limitation extends to the initial conditions of the universe itself. The Big Bang theory describes the evolution of the universe from a hot, dense state, but it doesn't address how or why the universe began with those particular initial conditions. Various theoretical approaches, including quantum cosmology and string theory, offer potential explanations, but these remain beyond direct observational confirmation. The universe we will never know, thus, includes not just regions of space beyond our horizon, but epochs of time forever hidden from direct view. The earliest moments of cosmic history, when the fundamental forces separated and the basic building blocks of matter formed, remain invisible to us, knowable only through theoretical extrapolation rather than direct observation. This temporal horizon combines with the spatial horizon to create a fundamental boundary to our knowledge of the cosmos. We can see neither infinitely far nor infinitely back in time. Our cosmic vision begins with the cosmic microwave background, roughly 380,000 years after the Big Bang, and extends outward to a horizon currently about 46 billion light-years in radius. Beyond these boundaries lies the universe we will never know. Yet this invisible cosmos is not entirely beyond our comprehension. Through theoretical models, computer simulations, and indirect evidence, we can infer much about what lies beyond our observational limits. The patterns we observe in the visible universe allow us to extrapolate to what might exist beyond, much as a naturalist might infer the presence of unseen species by the ecological niches they occupy or the traces they leave behind. The homogeneity and isotropy of the cosmic microwave background radiation suggest that the universe is largely uniform on the largest scales. The distribution of galaxies and the cosmic web of filaments and voids exhibit statistical patterns that likely extend beyond our cosmic horizon. By assuming these patterns continue, we can model what the unseen universe might look like, even if we can never directly observe it. Similarly, our understanding of fundamental physics allows us to model the earliest moments of the universe, epochs before the cosmic microwave background formed. Quantum field theory, general relativity, and other foundational theories provide frameworks for understanding how the universe evolved from its initial conditions, even if those conditions themselves remain partly mysterious. By testing these theories against what we can observe, we gradually refine our understanding of what we cannot directly see. But these inferences and extrapolations have inherent limitations. They rely on the assumption that the patterns and processes we observe in the visible universe extend to the invisible regions beyond. If the universe beyond our horizon contains fundamentally different physics or structures, our models might not apply. We would have no way to detect such cosmic variations directly. This creates a fundamental uncertainty in our understanding of the cosmos. The universe we will never know represents not just an observational limitation, but an epistemological boundary to what we can ever know with certainty about the totality of existence. Beyond our cosmic horizon lies not just unseen stars and galaxies, but potentially unseen laws of nature, unseen dimensions, unseen possibilities that remain forever beyond our direct investigation. Consider the fundamental constants of nature: the strength of gravity, the charge of an electron, the mass of a proton, the speed of light. In our observable universe, these constants appear, well, constant the same everywhere we look, and throughout cosmic history, as far as we can tell. But theoretical models, including some versions of string theory, suggest these constants might vary in regions beyond our cosmic horizon. If such variations exist, they would remain forever undetectable through direct observation. We might infer their possibility through theoretical models, but we could never directly measure these variations or map their distribution across the unseen cosmos. This represents another aspect of the universe we will never know: potential variations in the very laws of physics that govern reality. The dark sectors of the cosmos represent another category of the unknown. Dark matter, making up about 27% of the energy content of the universe, reveals itself only through its gravitational effects on visible matter. Dark energy, making up about 68%, manifests as the accelerating expansion of space. Together, they constitute 95% of the cosmos, yet their fundamental nature remains mysterious. We can detect the effects of dark matter and dark energy within our observable universe, but we cannot directly observe these phenomena themselves. They remain hidden aspects of the cosmos, known only through their gravitational influence rather than any form of electromagnetic radiation. In this sense, they represent a different kind of invisibility, not hidden beyond our cosmic horizon, but hidden within our observable universe, invisible to our current means of detection. The universe we will never know thus includes not just what lies beyond our spatial and temporal horizons, but what lies hidden within them: phenomena that do not interact with light or other forms of electromagnetic radiation, remaining invisible to our telescopes regardless of their power or sensitivity. Some theoretical models suggest the existence of mirror matter or shadow matter, forms of matter that interact with gravity, but not with electromagnetism or the other fundamental forces. Such matter would remain forever invisible to conventional observation, detectable only through its gravitational effects. If it exists primarily in regions beyond our cosmic horizon, we might never detect even these indirect effects. Similarly, some versions of string theory and other approaches to quantum gravity propose the existence of extra dimensions beyond the 3 spatial and 1 temporal dimension we experience. These additional dimensions, if they exist, might be compactified, curled up so tightly that they remain undetectable at the energies available to our experiments. or they might extend beyond our cosmic horizon, creating variations in physics that we can never directly observe. The universe we will never know might also include regions where the very geometry of space differs from what we observe. General relativity describes how matter and energy curve space-time, creating what we perceive as gravity. Different distributions of matter and energy create different curvatures. Beyond our cosmic horizon, the large-scale geometry of space might differ from the approximately flat geometry we observe in our visible universe. If the total universe is finite but unbounded, like the surface of a hypersphere in four-dimensional space, then regions beyond our horizon would eventually loop back toward us. But due to the accelerating expansion of the universe, light from these regions would never complete the journey. The geometry of the entire cosmos would remain forever partly hidden from our view. This geometric unknowability extends to the topology of the universe, the way space connects to itself on the largest scales. Our observable universe appears to have a simple topology, with no evidence of connections that would allow light to take multiple paths between distant points. But the total universe might have a more complex topology, with connections or structures that remain forever beyond our observation. The universe we will never know includes not just stars, galaxies, and other forms of matter and energy, but the very structure of space and time itself, beyond our cosmic horizon. It includes potential variations in physics, geometry, and topology that would fundamentally alter our understanding of reality if we could somehow observe them directly. Yet despite these profound limitations to our cosmic vision, we continue to explore, to observe, to theorize, to extend our understanding of the universe, both visible and invisible. We push against the boundaries of the observable, developing more powerful telescopes, more sensitive detectors, more sophisticated analysis techniques that extract every possible bit of information from the light that does reach us. We develop theoretical models that bridge the gap between the observable and the unobservable, using the patterns and processes we can see to infer what might exist beyond our horizon. We test these models against new observations, gradually refining our understanding of the cosmos and its evolution. In this ongoing quest for cosmic understanding, we are like mapmakers charting an infinite territory from a fixed vantage point. We can see only a finite region around us, but we can infer the nature of what lies beyond based on the patterns we observe within our horizon. Our cosmic map remains forever incomplete, yet it grows more detailed and more accurate with each new observation, each theoretical insight, each computer simulation. The universe we will never know reminds us of the limits to human knowledge, the boundaries beyond which direct observation cannot take us. It humbles us, showing that reality extends far beyond what we can directly perceive, that the cosmos is vaster and potentially more varied than our observations alone can reveal. Yet this invisible cosmos also inspires us, challenging us to develop new ways of understanding what cannot be directly seen. It pushes us to refine our theories, to seek indirect evidence, to use mathematics and logic, to extend our cosmic vision beyond the limits of observation. In this way, the universe we will never know becomes not just a limitation, but a frontier, not just a boundary to our knowledge, but an invitation to explore new paths to understanding. It reminds us that science is not just about what we can see directly, but what we can infer, model, and comprehend through the combination of observation, theory, and imagination. As we gaze at the night sky, we might reflect that for every star we can see, countless others exist beyond our cosmic horizon, forever invisible to us. They shine in the darkness, part of the same cosmic whole that includes our observable universe, connected through the same fundamental physics, even if no direct signal can ever pass between us. This unseen cosmos, though beyond direct observation, enriches our understanding of reality. It reminds us that existence is not limited to what we can directly perceive, that the universe extends far beyond the boundaries of our vision into realms we can comprehend intellectually, even if we cannot observe them directly. The universe we will never know is not a void or an absence, but a presence beyond our sight, a continuation of the same cosmic story that unfolds within our observable bubble. It's a story we can never read in full, yet one we can appreciate in its grandeur and complexity, even with only a fragment visible to our cosmic gaze. Throughout our cosmic journey, we've explored the many stars we will never see, those too distant, those hidden by dust, those whose light will never reach us, those that died before we could observe them, and those that never existed at all. We've confronted the limits of our cosmic vision, the boundaries beyond which direct observation cannot take us. But now we must ask a fundamental question. Why do these unseen stars matter? What significance do they hold if we can never directly observe them? The answer begins with gravity. The unseen stars, galaxies, and other cosmic structures exert gravitational influence that shapes the visible universe. Gravity acts across all distances, unhindered by cosmic horizons or interstellar dust. The gravitational field of every mass in the universe, seen or unseen, extends throughout all of space, affecting the motion and distribution of everything else. The large-scale structure of our observable universe, the cosmic web of galaxy filaments and voyages, been shaped partly by gravitational influences from beyond our cosmic horizon. During the early universe, before inflation pushed most of the cosmos beyond our future observation, regions now separated by billions of light years were close enough to influence each other gravitationally. The seeds of cosmic structure were planted during this early epoch of causal connection. Even today, the gravitational pull of masses beyond our cosmic horizon affects the overall expansion and geometry of the observable universe. While we cannot see these distant masses directly, their collective gravitational effect contributes to the total mass-energy content of the cosmos, influencing its curvature and evolution. Within our galaxy, unseen stars hidden by dust clouds affect the orbital dynamics of the visible stars around them. Their gravitational pull reveals their presence even when their light cannot reach us directly. The same principle applies to dark matter, which we detect primarily through its gravitational effects on visible matter. The unseen stars also matter because they contribute to the total energy and matter content of the universe. The cosmic microwave background radiation, our most distant observable remnant of the early universe, shows that the universe is remarkably flat. Its geometry, neither significantly positively nor negatively curved on the largest scales. This flatness requires a precise balance between the universe's expansion rate and its total density of matter and energy. The matter and energy beyond our cosmic horizon contribute to this total density, helping to determine the overall geometry and fate of the cosmos. Though invisible to us, they remain part of the same interconnected whole that includes our observable universe, governed by the same physical laws and contributing to the same cosmic evolution. The unseen stars also matter as sources of the elements that make up our visible universe. The first generation of stars, forming from primordial hydrogen and helium shortly after the cosmic dark ages, produced the first heavy elements through nuclear fusion and supernova explosions. These elements, carbon, oxygen, nitrogen, iron, and others essential to life as we know it, were dispersed through space, enriching the gas from which subsequent generations of stars would form. Many of these early stars existed in regions now beyond our cosmic horizon, or lived and died too quickly for their light to reach us. Yet the elements they created have spread throughout the cosmos, including into our observable region. The atoms in your body, the carbon in your cells, the oxygen you breathe, the iron in your blood, were forged in stellar furnaces, some perhaps in stars we will never see. This elemental legacy connects us to the unseen stars, making them part of our cosmic heritage, even if we cannot observe them directly. As Carl Sagan famously noted, we are made of star-stuff atoms assembled in stellar cores and scattered through space by stellar deaths. Some of that star stuff came from stars forever invisible to us, yet integral to the chemistry that makes our existence possible. The unseen stars also matter scientifically, challenging us to develop theories and models that extend beyond what we can directly observe. They remind us that science is not limited to what we can see with our eyes or our instruments, but encompasses what we can infer, deduce, and understand through the combined power of observation, theory, and mathematics. Cosmology in particular deals largely with the unseen with the early universe, before it became transparent to light, with dark matter and dark energy that don't interact directly with our detectors, with regions beyond our cosmic horizon that we can never directly observe. Yet these invisible aspects of the cosmos are essential to our scientific understanding of reality. By developing theories that account for both the seen and the unseen, scientists create more comprehensive and coherent models of the universe. These models predict phenomena that we can test through observation within our cosmic horizon, gradually refining our understanding of the invisible through its connections to the visible. For instance, inflation theory, which posits an exponential expansion in the earliest moments of the universe, predicts specific patterns in the cosmic microwave background radiation that we can observe directly. By confirming these predictions, we gain confidence in the theory's implications for what exists beyond our observable universe. Similarly, theories of stellar evolution and nucleosynthesis tell us about stars we cannot see directly, those obscured by dust, those that died before we could observe them, those too distant for their light to have reached us. By testing these theories against the stars we can observe, we extend our understanding to those we cannot. The unseen stars also matter philosophically, expanding our conception of reality beyond what we can directly perceive. They remind us that existence does not depend on observation, that the universe continues beyond the boundaries of our vision, that reality is not limited to what human eyes or instruments can detect. This expanded cosmic perspective challenges anthropocentric views that place humanity at the center of existence. The stars we will never see exist, regardless of whether we can observe them, their reality independent of our perception. They remind us that the universe does not exist for us or because of us, but we exist as a small part of a much larger cosmic whole, most of which remains forever beyond our direct observation. Yet this perspective need not diminish us. Instead, it can inspire a sense of wonder and connection to something larger than ourselves. The knowledge that we are part of a cosmos that extends far beyond what we can see, that our atoms were forged in stellar furnaces, both visible and invisible to us, can create a profound sense of cosmic citizenship. The stars we will never see also matter emotionally and aesthetically, filling us with wonder at the vastness and mystery of the cosmos. There is something poignant and beautiful about light traveling through the void for billions of years, carrying information about distant stars and galaxies, only to miss Earth by cosmic margins due to the expansion of space. There is poetry in the notion of stars that lived and died before our planet formed, their light still traveling through space, perhaps never to be seen by any conscious observer. There is a cosmic melancholy in considering galaxies now moving beyond our horizon, sending their final signals before disappearing forever from our potential observation. These emotions, wonder, awe, melancholy, curiosity, enrich our experience of the cosmos, connecting us to it not just intellectually, but emotionally. The unseen stars expand our emotional universe just as they expand our conceptual one, allowing us to feel something for what we cannot directly observe. The stars we will never see also matter practically, informing our understanding of cosmic evolution and the long-term fate of the universe. By modeling the unseen regions beyond our horizon, cosmologists can better predict the future of cosmic expansion, the eventual fate of star formation, and the ultimate destiny of the cosmos. If we understand what exists beyond our cosmic horizon and how it affects the overall evolution of the universe, we gain insight into our own cosmic future. Will the expansion of the universe continue to accelerate, eventually tearing apart galaxies, solar systems, and even atoms in a big rip? Will it continue steadily, leading to a big freeze as stars exhaust their fuel and the universe grows cold and dark? Or might some yet unknown physics eventually reverse the expansion, leading to a big crunch where all matter reconverges? These questions about cosmic destiny depend partly on what exists beyond our observation, on the total energy content of the universe, on the true nature of dark energy, on factors we can model but never directly observe. The unseen stars contribute to this cosmic calculus, their combined mass and energy helping to determine the ultimate fate of the universe. The stars we will never see also matter for potential civilizations beyond Earth. If other intelligent species exist in distant galaxies, they too are limited by cosmic horizons, by the finite speed of light, by the dust and gas that obscure portions of their view. They observe a different bubble of the observable universe, centered on their location, with different stars visible and invisible to them. Some stars invisible to us may be visible to them, and vice versa. Our Sunday may be one of the stars they will never see, just as countless stars in their vicinity remain forever invisible to us. This creates a kind of cosmic democracy of perspective, where no single viewpoint encompasses the entire universe, where the seen and the unseen depend on one's location in space and time. If intelligent life is common in the cosmos, then most civilizations probably exist in galaxies we will never see, beyond our cosmic horizon, or hidden by dust and gas. Their histories, their discoveries, their art and music and philosophy, their unique perspective on the cosmos remain forever unknown to us, separated by distances too vast for light to cross within the age of the universe. Yet we share the same fundamental reality, governed by the same physical laws, composed of atoms forged in similar stellar furnaces, evolving in a universe with the same cosmic history. Though we can never communicate or meet, we are part of the same cosmic story, connected by our shared origin in the Big Bang and our common subjection to the laws of physics. This connection to potential civilizations we will never contact adds another dimension to the significance of the unseen stars. They may host countless worlds, countless forms of life, countless perspectives on the cosmos different from our own. The invisible majority of the universe may contain most of its conscious observers, most of its civilizations, most of its interpretations of existence. The stars we will never see also matter because they contextualize our knowledge, reminding us of its incompleteness. When we build models of cosmic evolution, when we analyze the distribution of galaxies, when we calculate the total mass-energy content of the universe, we necessarily work with a limited sample of the observable universe. Yet this sample represents just a fraction of the whole, possibly an infinitesimal fraction if the universe is infinite. How representative is our cosmic neighborhood of the totality? Do the patterns we observe continue beyond our horizon? Do the physical laws we've discovered apply everywhere and everywhen? The unseen stars raise these questions, challenging the universality of our knowledge. Yet they also provide a framework for extending our understanding beyond what we can directly observe. By recognizing the limits of our cosmic vision, we can develop more sophisticated models that account for both the seen and the unseen. We can use the patterns within our horizon to infer what might exist beyond, gradually building a more comprehensive understanding of the cosmos. The stars we will never see also matter because they sharpen our appreciation for what we can see. The knowledge that most of the universe remains forever hidden from direct observation makes the visible cosmos all the more precious. Each photon that reaches our telescopes from a distant galaxy has completed an improbable journey, traversing billions of light-years of expanding space to bring us information about regions we can still observe. This light represents a cosmic connection, a thread linking us to distant regions of space and time. The photons striking our detectors physically connected with the stars that emitted them, carrying information across the vast cosmic gulf to reach our instruments. This physical connection, this sharing of energy across space and time, creates a tangible link between observer and observed. In contrast, the stars beyond our cosmic horizon can never establish this physical connection with us. No particle, no wave, no influence of any kind can cross from them to us or from us to them. This absolute separation makes our connection to the observable universe all the more significant, a genuine physical relationship rather than merely a conceptual one. The unseen stars also matter because they provide context for our cosmic location. The observable universe appears remarkably homogeneous and isotropic on the largest scales, with matter distributed relatively uniformly in all directions. This cosmic uniformity suggests that our location is not special or privileged, that observers elsewhere would see a similar cosmic panorama, though centered on their location, rather than ours. The stars beyond our horizon likely forms similar patterns to those within it. The same cosmic web of galaxy filaments and voids, the same clustering of galaxies into groups and superclusters, the same basic processes of stellar birth, life, and death. This cosmic continuity places our observable universe in context, not as a unique or special region, but as a representative sample of a much larger whole. Understanding this context helps us avoid the historical error of assuming cosmic centrality. From ancient geocentric models that placed Earth at the center of creation to more recent attempts to identify our location as somehow special or unique, human thought has often struggled to accept cosmic mediocrity. The stars we will never see remind us that the cosmos extends far beyond our observation, that our perspective is limited and partial, that we occupy no privileged position in the grandeur of space. Yet they also remind us of the special role of observers in the cosmos. Without conscious minds to detect them, the stars remain energy and matter conforming to physical laws, their beauty and significance unrealized. It is through observation and comprehension that the cosmos becomes meaningful, that patterns emerge from data, that the universe knows itself through the minds that evolved within it. In this sense, the stars we will never see represent the universe's unrealized potential for observation and comprehension. If no conscious observers ever evolve in those distant regions, if no minds ever contemplate the cosmos from those far-flung galaxies, then much of existence remains forever unobserved, its patterns unrecognized, its beauty unappreciated. This possibility gives our cosmic vision, limited though it is, profound significance. We may be able to observe only a fraction of the universe, but that fraction becomes meaningful through our observation. The patterns we discern, the laws we discover, the beauty we appreciate, these transformations of raw data into understanding, represent the universe comprehending itself through us. The stars we will never see remind us of how much remains beyond our vision, challenging us to extend our understanding through theory and inference. But they also highlight the value of what we can see, the privilege of being cosmic observers, the remarkable fact that the universe has evolved minds capable of contemplating its vastness and structure. In the end, the unseen stars matter because they are real. They exist regardless of our ability to observe them directly. They burn in the darkness, fusing hydrogen into helium, synthesizing heavier elements, ending their lives in supernovae, or planetary nebulae, or gradual cooling, all beyond our cosmic horizon. Their reality is independent of our perception, yet connected to our understanding of the cosmos. By acknowledging what we cannot see, we develop a more complete and accurate understanding of what we can. By modeling the unseen based on the seen, we extend our cosmic comprehension beyond the limits of direct observation. By appreciating the vastness of what lies forever hidden, we gain a more profound perspective on our place in the cosmos. The stars we will never see are as much a part of our cosmic story as those that grace our telescopes and our night sky. They exist within the same web of physical laws, born from the same initial conditions, evolving according to the same fundamental processes. Though invisible to us, they remain essential to our comprehensive understanding of the universe that surrounds us, encompasses us, and created us. As we look outward at the visible cosmos, we might remember that what we see represents just a fraction of what exists. Beyond our vision, beyond our horizon, beyond even our theoretical grasp in some ways, the universe continues vast, ancient, largely unseen, yet profoundly connected to the small bubble of space and time that we can directly observe. The unseen stars remind us that reality extends far beyond perception, that existence does not depend on observation, that the cosmos is even grander, more complex, and more mysterious than what meets our eyes or our telescopes. Throughout our journey, we've focused on the stars we will never see, those hidden from our view by distance, time, cosmic expansion, and interstellar dust. But there's another perspective to consider, one that shifts our viewpoint from Earth outward to looking back at ourselves from the depths of space. What about the civilizations that may exist around distant stars? From their perspective, our Sunday might be one of the stars they will never see. Or perhaps in some far distant future, Light from our solar system will eventually reach their telescopes, carrying information about Earth and humanity long after we're gone. This cosmic reversal of perspective reminds us that the limitations of light's speed and the expansion of space affect all observers throughout the universe. Just as we can observe only a limited bubble of space-time centered on Earth, potential observers elsewhere can see only their own observable bubbles. These bubbles overlap but aren't identical. Stars visible to us may be invisible to them, and vice versa, depending on their location and time. Consider an intelligent civilization evolving today on a planet orbiting a star in a galaxy 10 billion light-years away. From their vantage point, they wouldn't see our current Milky Way galaxy or our Sunday as they exist today. Instead, they would observe our galaxy as it was 10 billion years ago, long before our Sunday had formed, when the universe was less than 4 billion years old. Our solar system, Earth, and humanity would be invisible to them, not yet having come into existence in the early universe they observe. Conversely, when we look toward their galaxy, we see it not as it is today, but as it was 10 billion years ago. We observe its light from a time before their star had formed, before their planet existed, before their civilization had evolved. We're each invisible to the other, separated not just by space but by time, by the finite speed of light that creates a cosmic look-back time proportional to distance. Yet the light that left Earth today will eventually reach their location, crossing the vast gulf of space over billions of years. If their civilization survives for 10 billion years, future generations might detect signals from present-day Earth, observing us as we are today. Similarly, if humanity or its successor intelligence survives for billions of years, we might eventually detect signals sent from their world today. This creates a strange form of one-way communication across cosmic time. By the time our signals reach a distant civilization, we might be long gone, our messages becoming fossilized transmissions from an extinct species. And by the time their response could reach Earth, their civilization might have disappeared as well. We would be like cosmic ships passing in the night, visible to each other only through light, sent across vast gulfs of time, never truly contemporaneous in our observations. For civilizations beyond our cosmic horizon, even this delayed communication becomes impossible. Light from present-day Earth will never reach regions moving away faster than light due to cosmic expansion. Similarly, no signal from beyond our horizon, no matter when it was sent, can ever reach us. The accelerating expansion of the universe creates absolute boundaries to potential communication, regions of space permanently invisible to each other. Yet for stars and galaxies within our cosmic horizon, but currently too distant for their light to have reached us, future communication remains possible. Light from Earth is traveling outward at 300,000 kilometers per second, gradually reaching more distant regions of space. With each passing year, with each passing century and millennium, Earth becomes visible from more distant vantage points as our light completes its journey to more remote locations. Imagine the expanding bubble of Earth's visibility, centered on our planet and growing at the speed of light. This bubble represents all regions of space that could potentially observe Earth, that have received at least some light from our world. The edge of this bubble is currently about 13.8 billion light-years in radius, the age of the universe multiplied by the speed of light. At the very edge of this visibility bubble, observers with sufficiently powerful telescopes could just now be detecting the first light from the formation of Earth, about 4.5 billion years ago. From their perspective, they would see not a life-bearing planet, but a young, molten world, still cooling from its formation, still being bombarded by asteroids and comets, its atmosphere not yet oxygen-rich, its surface not yet hospitable to complex life. Slightly closer observers, perhaps 10 billion light-years distant, might now be seeing light from Earth during the early evolution of life single-celled organisms, just beginning to transform our planet's atmosphere. The first experiments with photosynthesis, the earliest diversification of primitive life forms. They would observe an Earth no human would recognize, billions of years before our species evolved. Closer still, observers 5 billion light-years away might now be detecting light from Earth during the time of the dinosaurs. They would see a world dominated by reptilian megafauna, landmasses in different configurations due to continental drift, an atmosphere with different composition than today. They would have no indication that an intelligent, technological species would eventually evolve on this distant planet. Only observers within about 100,000 light-years roughly, the diameter of our Milky Way galaxy, could potentially detect signs of human civilization. More distant observers would see Earth before humanity had evolved, or before we had developed technology capable of modifying our planet in ways detectable across interstellar or intergalactic distances. Even within this relatively local bubble, few observers would see present-day Earth with its current technology and population. Most would see our world as it was decades, centuries, or millennia ago, depending on their exact distance. Only our nearest stellar neighbors, within a few dozen light-years, would observe Earth as it has existed during the modern technological age. This expanding bubble of Earth's visibility will continue to grow as long as our planet exists and emits or reflects light. Long after humanity is gone, long after Earth itself has been transformed by geological and astronomical processes, light carrying information about our present era will continue its journey outward, potentially reaching more distant observers in the far future. In about 2 billion years, light from present-day Earth will reach the Andromeda Galaxy, our closest large galactic neighbor. If intelligent observers exist there at that future time, they might detect signs of our civilization, analyzing the spectrum of light from our planet to determine its atmospheric composition, perhaps detecting the chemical signatures of our industrial activity, the modified atmosphere that bears the imprint of technological life. By this time, Earth itself will have changed dramatically. Our Sunday will be nearing the end of its main sequence life, growing hotter and larger, potentially making Earth uninhabitable. Humanity, if it still exists, might have evolved into different forms, might have migrated to other worlds, might have transformed into a post-biological intelligence, unlike anything we can currently imagine. Yet the light leaving Earth today preserves a record of our current world, carrying it across space to potential future observers. Long after we're gone, this light will continue its journey, a fossil record of our time encoded in photons traveling at the universe's fundamental speed limit. In this way, humanity might eventually be observed by civilizations in distant galaxies, not as we are when they detect us, but as we were billions of years earlier, when the light left Earth. We would be, for them, an ancient civilization, perhaps long extinct, known only through the electromagnetic signals that continue to traverse the cosmos long after their origin point has changed beyond recognition. This perspective shifts our understanding of cosmic visibility. We tend to think of distant stars and galaxies as the ones we will never see. But from the viewpoint of potential observers throughout the cosmos, we are among the stars they will never see, least not as we exist today. By the time our light reaches very distant observers, both we and Earth may be radically transformed or gone entirely. Consider observers in a galaxy 20 billion light-years away in terms of current proper distance. Light from Earth today will never reach them due to cosmic expansion. They exist beyond our cosmic horizon, and we beyond theirs. Our civilizations are permanently invisible to each other, not just now but forever. No signal, no message, no information of any kind can ever cross the expanding gulf between us. Closer observers, say 10 billion light-years distant, might eventually receive light from present-day Earth, but not for another 10 billion years. By that time, our Sunday will have expended its nuclear fuel, swollen into a red giant, and then collapsed into a white dwarf. Earth, if it still exists at all, will be a scorched, lifeless world, having long since lost its atmosphere and oceans to the sun's expanded reach. Would these distant future observers, detecting signals from our long-vanished civilization, wonder about us? Would they analyze our light for signs of technology, for indications of our biology? for clues about our understanding of the universe? Would they recognize us as kindred intelligences despite evolving billions of years and billions of light years apart? Perhaps they would search for patterns in our transmissions, attempting to decode our languages, to understand our science, to glimpse our art and culture through the electromagnetic signals that continue to travel across the cosmos long after our civilization has disappeared. We would be, for them, a mystery from the distant past, a civilization they can observe, but never contact, whose fate they can only speculate about. In a sense, we might become for them what ancient civilizations are for us subjects of archaeological interest, cultures whose physical remains and written records provide windows into past ways of thinking and living. But unlike terrestrial archaeology, these distant observers would have no way to visit the sites of our civilization, to excavate our cities, to examine our artifacts directly. They would have only the light that left Earth during our time, carrying limited information about our world and our species. This cosmic archaeology might become a common activity for long-lived civilizations throughout the universe. By observing light from increasingly distant regions, they could witness cosmic history unfolding, including the rise and perhaps fall of other technological species. They would build a catalogue of detected civilizations, most likely extinct by the time they're observed, due to the vast distances involved. Our own civilization might eventually join this catalogue, one data point in a cosmic census of intelligence. We might be classified, categorized, analyzed by beings we cannot imagine, in a future so distant that the very stars would have rearranged themselves in the night sky. Our signals, our transmissions, our modifications to Earth's atmosphere and surface, these might become our unintentional legacy, a time capsule traveling eternally through space, long after we're gone. There's something both humbling and profound about this possibility. Our existence, brief as it might be on cosmic timescales, leaves an electromagnetic shadow that expands outward at the speed of light, potentially observable billions of years into the future, by beings, on worlds, we will never know existed. Though we might disappear, this record of our having been here continues its journey through space, a testament to our momentary presence in the cosmic story. Of course, deliberate attempts at communication could supplement this incidental evidence of our existence. Radio transmissions, powerful laser signals aimed at specific star systems, or other intentional messages might provide clearer evidence of our intelligence than the passive light reflected from Earth's surface or filtered through its atmosphere. Organizations like METI, Messaging Extraterrestrial Intelligence, have already begun such efforts, sending deliberate signals to nearby star systems that might host habitable worlds. These signals, designed to be recognizable as artificial, travel outward at light speed, gradually reaching more distant regions of space. Unlike general radio and television broadcasts, which quickly become too faint to detect against the cosmic background, these focused transmissions might remain detectable across much greater distances. If humanity continues such efforts over centuries or millennia, gradually increasing the power and sophistication of our transmissions, we might eventually create a more substantial electromagnetic presence in the galaxy, one more likely to be detected by distant observers. Our deliberate messages might outlast our civilization, continuing to announce our having existed long after we ourselves are gone. Yet even these intentional signals face the same fundamental limits as all electromagnetic radiation. They cannot exceed the speed of light, and they cannot cross beyond the cosmic horizon created by the accelerating expansion of the universe. They can reach only those civilizations within our cosmic bubble, those not moving away faster than their light can travel toward us through expanding space. For civilizations beyond this horizon, we will forever remain among the stars they will never see. And they, for us, will remain permanently invisible, regardless of how powerful our telescopes become or how long we wait for their light to reach us. The accelerating universe creates absolute, permanent boundaries between different regions of space, cosmic neighborhoods that can never communicate or interact. This cosmic isolation reminds us that for all the vastness of the potentially habitable universe, only a fraction remains causally connected to Earth. Only within this connected region could we ever hope to be observed by, or ourselves observe, other intelligent life. Beyond our cosmic horizon, countless civilizations might exist, evolving, flourishing, perhaps wondering like us whether they are alone in the universe, yet forever beyond our ability to detect or contact. Even within our causally connected region, the vast majority of potential observers would see Earth not as it is today, but as it was in the distant past. Only our nearest neighbors could observe anything resembling current human civilization, and even they would see us as we were years or decades ago, depending on their exact distance. As we look out at the cosmos then, we might remember that we too are among the stars that others will never see, at least not as we exist today. Our light travels outward, carrying information about our world and our species to potential observers throughout space and time. But for most of those potential observers, that light has not yet arrived or never will arrive. We are, for them, either stars not yet seen or stars that will never be seen, invisible not through any property of our own, but through the fundamental limits imposed by the finite speed of light and the expansion of space. This cosmic perspective shift helps us understand our place in the universe in a new way. We are not just observers of distant stars and galaxies. We are also potentially observed, our light traveling outward to unknown destinations, carrying the story of Earth and humanity to worlds we will never know existed. We are both the watchers and the watched, both the seers and the seen, part of the great cosmic web of potential observation that connects all regions within each other's cosmic horizons. If we imagine a map of the universe with lines connecting all potential observers with what they can potentially see, we would find a vast, intricate network of one-way and two-way connections. Nearby regions can observe each other with relatively short delays. More distant regions observe each other as they were in the increasingly remote past. Beyond certain distances, connections become one-way due to cosmic expansion, with more distant regions able to observe closer ones, but not vice versa. Earth occupies one node in this vast network, sending and receiving light according to the same physical laws that govern all electromagnetic radiation throughout the cosmos. Our transmissions, both intentional and incidental, travel outward along these connections, potentially reaching other nodes where intelligent observers might detect them, analyze them, perhaps even understand something of their origin and meaning. In this sense, we are not just passively illuminated by distant stars. We ourselves are a star that may one day be seen by distant observers. Our Sunday, a relatively unremarkable G-type main sequence star, one of hundreds of billions in our galaxy alone, might eventually be noted by astronomers on planets orbiting other stars, catalogued, perhaps even recognized as hosting a technological civilization during a brief period of its history. This recognition might come long after that civilization has disappeared, long after Earth itself has been transformed by the evolution of its star. The light containing evidence of our existence would reach distant observers billions of years after the events it records, like a message in a bottle washing ashore centuries after the shipwrecked sailor who cast it adrift has perished. Yet this delayed observation still matters. It connects regions of space and time that could never interact directly, creating a form of cosmic memory, a record of what existed, preserved in the light that continues its journey long after its source has changed or vanished. In this way, the stars that may one day see us expand the reach of our existence beyond our physical presence, beyond even the survival of our species or our planet. This perspective offers a kind of cosmic immortality, not of consciousness or identity, but of information, of evidence that we were here. Long after humanity is gone, photons carrying information about our world will continue their journey through space, potentially reaching observers in distant galaxies in the far future. Our existence leaves an expanding bubble of visibility, a light-speed shadow that grows outward for as long as light can travel through the cosmos. And perhaps, in some distant future, observers on a world we will never know existed will detect these signals, will recognize the chemical signatures of a technological civilization, will wonder about us as we wonder about potential intelligences around distant stars. In that moment of recognition, across a gulf of space and time so vast we can barely comprehend it, a connection would form, not communication, but awareness, not conversation, but acknowledgement of another's existence. In this way, the stars that may one day see us remind us that our cosmic story continues long after we ourselves are gone, carried by light to distant worlds, witnessed perhaps by observers we can never know or contact. We are not just transient beings in a vast cosmos, but contributors to an ongoing exchange of light and information that connects regions of space-time across billions of light years and billions of years. As we look up at the night sky then, we might remember that we are not just seeing stars, we are stars being seen, or that may one day be seen. Our light joins the great cosmic conversation, the silent exchange of photons that connects all regions within each other's cosmic horizons. We are both readers and authors of the cosmic story, both audience and performers in the great electromagnetic symphony that fills the universe. This dual role as both observers and observed gives us a more complete understanding of our place in the cosmos. We are not separate from the universe we study, but integral to it. Not just recipients of cosmic light, but sources of it, part of the same interconnected web of visibility and invisibility that encompasses all regions of space and time within the expanding universe. And so, as we contemplate the stars we will never see, we might also reflect on the civilizations that will never see us, on the light from Earth that will never reach distant galaxies beyond our cosmic horizon, on the fundamental limits to visibility that affect all observers throughout the cosmos. We might recognize that we too are among the unseen stars for much of the universe, invisible not through any property of our own, but through the basic physics of light and expanding space. Yet we might also imagine the expanding bubble of Earth's visibility, growing outward at the speed of light, gradually reaching more distant regions of space, potentially being observed by civilizations on worlds we will never know existed. We might picture future astronomers on planets orbiting distant stars, detecting signs of our long-vanished civilization, wondering about us as we wonder about them, connected across the gulf of time and space by the light that carries information from each to the other. In this ongoing exchange of cosmic light, in this silent conversation carried by photons across billions of light years and billions of years, we find perhaps the truest expression of our place in the universe, not as its center or its purpose, but as participants in its vast, intricate network of potential observation, as both watchers and watched in the great cosmic story that encompasses all stars, seen and unseen. Though we may never directly observe many stars in our universe, their influence reaches us in subtle, indirect ways that transcend the limitations of light. Like whispers carried on a distant wind, these cosmic echoes bring us information about realms beyond our direct vision, connecting us to the unseen through the invisible threads of physics that bind the universe together. Perhaps the most profound of these connections comes through gravity. Unlike light, which travels at a finite speed through space, gravity is not so much a signal that propagates as it is a curvature of space-time itself. The gravitational influence of every mass in the universe, seen or unseen, extends throughout all of space, creating a cosmic web of attraction that shapes the motion and distribution of everything else. The large-scale structure of our observable universe, the filaments and voids of the cosmic web, the clustering of galaxies into groups and superclusters bears the imprint of mass distributions, both visible and invisible to us. During the early universe, before inflation pushed most of the cosmos beyond our future observation, regions now separated by billions of light years were close enough to influence each other gravitationally. The seeds of cosmic structure were planted during this early epoch of causal connection. Even today, the collective gravitational pull of masses beyond our cosmic horizon affects the overall expansion and geometry of the observable universe. While we cannot see these distant masses directly, their cumulative gravitational effect contributes to the total mass energy content of the cosmos, influencing its curvature and evolution. The remarkable flatness of our observable universe as revealed by measurements of the cosmic microwave background radiation, depends on the total density of matter and energy throughout the cosmos, including regions we will never directly observe. Within our own galaxy, gravitational influences reveal the presence of stars and other masses hidden from direct view. The motion of visible stars can indicate the gravitational pull of unseen companions, leading to the discovery of binary systems, where one member remains hidden by distance or obscuration. The wobble of stars caused by orbiting planets has allowed astronomers to detect thousands of exoplanets, many orbiting stars too distant to resolve with current telescopes. On larger scales, the motions of stars within galaxies and of galaxies within clusters reveal the presence of dark matter-invisible mass that interacts only through gravity. Though we cannot see dark matter directly, its gravitational influence shapes cosmic structures at all scales, from the rotation curves of individual galaxies to the formation of the largest clusters and filaments in the observable universe. These gravitational echoes connect us to the unseen cosmos, allowing us to infer the presence and properties of matter we cannot directly observe. Through precise measurements of cosmic motions and distributions, astronomers can map not just the visible universe, but the invisible structures that shape it, creating a more complete picture of what exists beyond our direct vision. Another profound connection to the unseen stars comes through the elements that make up our world and our bodies. The first generation of stars, forming from primordial hydrogen and helium shortly after the cosmic dark ages, produced the first heavy elements through nuclear fusion and supernova explosions. These elements, carbon, oxygen, nitrogen, iron, and others essential to life as we know it, were dispersed through space, enriching the gas from which subsequent generations of stars would form. Many of these early stars existed in regions now beyond our cosmic horizon, or lived and died too quickly for their light to reach us. Yet the elements they created have spread throughout the cosmos, including into our observable region. The atoms in your body, the carbon in your cells, the oxygen you breathe, the iron in your blood were forged in stellar furnaces, some perhaps in stars we will never see. Each atom has its own cosmic history, a journey that may have begun in a star, now invisible to us, either through distance, time, or obscuration. The iron in your blood may have been created in a supernova explosion billions of years ago, in a galaxy now moved beyond our cosmic horizon by the expansion of space. The gold in a wedding ring might have been formed during the collision of neutron stars in a part of the cosmos now hidden behind interstellar dust clouds. This elemental legacy creates a physical connection between us and the unseen stars, making them part of our cosmic heritage, even if we cannot observe them directly. We are, in a very literal sense, made of star stuff atoms assembled in stellar cores and scattered through space by stellar deaths. Some of that star stuff came from stars forever invisible to us, yet integral to the chemistry that makes our existence possible. The cosmic rays that constantly bombard Earth represent another connection to distant and obscured regions of the universe. These high-energy particles, primarily protons and atomic nuclei, travel through space at nearly the speed of light. They originate from various sources, including the Sun, exploding stars, and distant active galactic nuclei, powered by supermassive black holes. Many cosmic rays come from sources we cannot directly observe, either because they're hidden by dust and gas, or because they're too distant for their light to have reached us yet. The particles themselves, being electrically charged, don't travel in straight lines but are deflected by magnetic fields in space, making it difficult to trace them back to their precise origins. Yet they bring us direct, physical evidence of energetic processes occurring throughout the cosmos, including in regions invisible to our telescopes. When a high-energy cosmic ray strikes Earth's atmosphere, it creates a cascade of secondary particles that can be detected by observatories on the ground. Each such detection represents a message from the distant cosmos, a particle that may have traveled for millions or billions of years before reaching our planet. These particles connect us physically to events that occurred in stars and galaxies we may never directly observe, creating a tangible link to the unseen universe. Neutrinos, nearly massless particles that rarely interact with ordinary matter, provide another window into otherwise invisible regions of space. Produced in enormous numbers by nuclear fusion in stellar cores, by supernovae, and by other high-energy cosmic processes, neutrinos travel through space essentially unimpeded, passing through dense matter as if it weren't there. Unlike light, which can be blocked by dust and gas, neutrinos reach us from sources that might otherwise remain hidden. The detection of neutrinos from supernova 1987A, a star that exploded in the Large Magellanic Cloud, provided astronomers with information about the inner workings of the explosion that couldn't be obtained from electromagnetic observations alone. Future neutrino observatories might detect signals from stars and galaxies hidden behind dust clouds, or even from the earliest moments of stellar collapse before light can escape. Because neutrinos interact so weakly with matter, detecting them requires enormous detector tanks containing thousands of tons of water or other materials buried deep underground to shield them from other particles. Yet each detection represents a direct, physical connection to distant cosmic processes, a particle that has traveled from its source directly to our detectors, without interference or absorption along the way. The cosmic microwave background radiation, the afterglow of the hot early universe, connects us to the earliest epoch of cosmic history. This faint radiation, pervading all of space, was emitted when the universe was just 380,000 years old, long before stars or galaxies had formed. It carries information about the conditions in the early universe, including regions now moved beyond our cosmic horizon by the subsequent expansion of space. The patterns in this radiation, tiny temperature fluctuations reflecting density variations in the early universe, contain information about the entire cosmos as it existed at that early time, including regions that are now forever invisible to us due to cosmic expansion. By studying these patterns, cosmologists can infer properties of the universe as a whole, including its geometry, composition, and evolution, gaining insights into what exists beyond our direct observation. Gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects, offer yet another connection to the unseen cosmos. Unlike electromagnetic radiation, gravitational waves pass through dust and gas, virtually unaffected, bringing us information about events that might otherwise remain hidden. The first detected gravitational waves, observed in 2015, came from the merger of two black holes, about 1.3 billion light-years away objects that emit no light and would have been invisible to traditional telescopes. Future gravitational wave observatories, both on Earth and in space, might detect signals from events throughout the cosmos, including those in regions obscured by dust or beyond the reach of our conventional telescopes. Each detection would represent a direct measurement of space-time distortion caused by distant massive objects, a physical connection to events occurring in parts of the universe we may never see directly. Even the vacuum of space itself connects us to the unseen cosmos. Quantum field theory tells us that seemingly empty space is actually filled with virtual particles constantly popping into and out of existence. These quantum fluctuations are influenced by the gravitational field of the entire universe, including masses beyond our cosmic horizon. The zero-point energy of these vacuum fluctuations contributes to the cosmological constant, a factor in the accelerating expansion of space. Some theories suggest that these quantum fluctuations in the vacuum are connected to the multiverse, the hypothetical set of all possible universes beyond our own. If such a multiverse exists, these subtle fluctuations might represent a tenuous physical link to realms even more profoundly separated from our observation than stars beyond our cosmic horizon. The interconnected nature of the cosmos ensures that no region is truly isolated, even if direct observation remains impossible. Through gravity, through the elements forged in stellar furnaces, through cosmic rays and neutrinos and gravitational waves, we maintain physical connections to stars and galaxies we will never see directly. These connections create a more complete picture of the universe, one that extends beyond the limits of light to encompass all that exists, seen and unseen. These cosmic echoes also challenge our understanding of observation itself. In classical physics, observation seemed straightforward. Light from an object enters our eyes or instruments, creating an image or measurement. But modern physics reveals a more complex relationship between observer and observed. Quantum mechanics introduces the concept of complementarity, where the act of observation affects what is observed. Relativity shows that different observers can perceive the same events differently depending on their reference frames. When we observe unseen stars through their gravitational effects, or through the elements they've created, we're engaging in a more indirect, but no less valid form of observation. We're detecting not the stars themselves, but their influences, their legacies, their contributions to the cosmic whole. This expanded understanding of observation allows us to develop a more comprehensive picture of the universe, one that includes not just what we can see directly, but what we can infer, deduce, and understand through multiple channels of information. For intelligent civilizations elsewhere in the cosmos, these same principles apply. They too would be limited by their cosmic horizons, by the finite speed of light, by the dust and gas that obscure portions of their view. Yet they too could detect the gravitational influence of masses beyond their direct observation, could analyze the elements in their worlds for clues about stellar nucleosynthesis in distant and hidden regions, could receive cosmic rays and neutrinos from sources invisible to their telescopes. This creates a kind of cosmic democracy of knowledge, where all observers throughout the universe are subject to the same physical laws and the same observational limitations. Each has access to their own observable bubble, centered on their location, with different stars visible and invisible to them. But each can also employ the same physical principles, the same indirect methods of observation, to extend their understanding beyond what they can see directly. If intelligent life is common in the cosmos, then most civilizations probably exist in galaxies we will never see, beyond our cosmic horizon, or hidden by dust and gas. Their histories, their discoveries, their art and music and philosophy, their unique perspective on the cosmos all, remain forever unknown to us, separated by distances too vast for light to cross within the age of the universe. Yet we share the same fundamental reality, governed by the same physical laws, composed of atoms forged in similar stellar furnaces, evolving in a universe with the same cosmic history. We're all subject to the same gravitational influences, all recipients of the same cosmic rays, all connected to the same web of causes and effects that shapes the universe as a whole. Though we can never communicate or meet, we are part of the same cosmic story. This shared reality extends even to civilizations beyond our cosmic horizon. Though no signal, no light, no information of any kind can cross the boundary created by accelerating cosmic expansion, we remain connected through our common origin in the Big Bang, through the physical laws that govern all regions of space and time, through the fundamental unity of the cosmos, despite its vastness and diversity. The echoes from beyond the void remind us that the universe is not just what we can see, but what we can know through all available channels of information. The unseen stars, though invisible to our direct observation, still matter in our understanding of the cosmos. Their gravitational influence, the elements they've created, the particles they've emitted all, contribute to the cosmic environment we inhabit and study. As our understanding of physics continues to evolve, we may discover new ways to connect with the unseen cosmos, new channels of information that extend our knowledge beyond current limitations. Just as the development of neutrino astronomy and gravitational wave detection has expanded our ability to observe previously invisible phenomena, future advances may reveal aspects of the universe currently hidden from our awareness. The history of astronomy has been a progressive revelation of the previously unseen. The invention of the telescope revealed stars too faint for the naked eye. The development of radio astronomy uncovered sources invisible in optical wavelengths. Infrared and ultraviolet astronomy extended our vision beyond the narrow band of visible light. X-ray and gamma-ray telescopes showed us the high-energy universe. Each new window into the cosmos has expanded our understanding, revealed previously hidden aspects of reality. This progression suggests that our current limitations may not be permanent, while the finite speed of light and the expansion of space create fundamental boundaries to direct observation. The cosmos continues to speak to us through multiple channels. By listening to all these cosmic voices, by attending to the echoes from beyond the void, we develop a richer, more complete understanding of the universe in all its seen and unseen glory. The unseen stars, though invisible to our telescopes, remain part of our cosmic story, connected to us through the invisible threads of physics that bind all regions of space and time. Their echoes reach us in subtle ways through gravity, through elements, through particles, through waves in space-time, itself reminding us that the universe extends far beyond what we can see directly. In these cosmic echoes, we find not just information about distant and hidden regions of space, but a more profound understanding of our place in the universe. We are not isolated observers of a separate reality, but integral participants in an interconnected cosmic whole. The stars we will never see are not truly separate from us, but part of the same physical reality, influencing and being influenced by the same fundamental forces that shape all of existence. As we continue our exploration of the cosmos, attending to both what we can see directly and what we can know indirectly, we develop a more complete picture of the universe, a picture that includes not just the visible stars that grace our telescopes and our night sky, but the invisible majority that remains hidden from direct view yet connected to us through the fundamental unity of the cosmos. We've explored the many stars hidden from our view by distance, time, dust, and cosmic expansion. We've considered how these unseen stars still influence our universe through gravity, elements, and other indirect channels. But to truly appreciate the cosmos in its entirety, we must venture beyond conventional human perspectives, beyond even the limitations of electromagnetic observation, to consider alternative ways of perceiving and understanding the universe. Imagine for a moment a form of intelligence that perceives gravity directly, as vividly as we perceive light. Such beings would experience the cosmos very differently than we do. Where we see points of light against the darkness, they would feel the gravitational pull of masses throughout space. Stars hidden behind dust clouds would be as perceptible to them as visible stars are to us. The dark matter that we can detect only indirectly would be immediately apparent. Its distribution throughout the cosmos, as evident as the distribution of visible matter, is to our eyes and instruments. For such gravity-perceiving beings, many of the stars we will never see would be directly perceptible. The limitations of electromagnetic observation, the obscuration by dust, the finite speed of light, the cosmic horizon created by expanding space, would not restrict their awareness in the same ways. They would experience a more complete cosmic perspective, one that encompasses both the visible and invisible aspects of the universe. Of course, such beings remain hypothetical, products of our imagination rather than entities we've observed. But considering such alternative perspectives helps us recognize the constraints of our own cosmic vision, the ways in which our particular sensory and cognitive apparatus shapes our understanding of the universe. It reminds us that what we call observation is always mediated by the specific channels through which we receive information, whether those channels are our biological senses or the instruments we design to extend them. Even within the realm of electromagnetic observation, our human perspective is limited. Our eyes evolved to detect a narrow band of wavelengths, what we call visible light, which represents just a tiny fraction of the electromagnetic spectrum. Without technology to extend our vision, we would remain unaware of the rich information carried by radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Each of these wavelength ranges reveals different aspects of the cosmos. Radio telescopes show us cool hydrogen gas and the remnants of exploded stars. Infrared telescopes pierce dust clouds to reveal stellar nurseries and the hearts of galaxies. X-ray telescopes detect the superheated gas around black holes and within galaxy clusters. By combining observations across the electromagnetic spectrum, astronomers build a more complete picture of the cosmos than any single wavelength range could provide. This multi-wavelength astronomy has revealed countless stars and other cosmic objects that would remain invisible if we relied solely on optical telescopes. It has shown us that the universe we perceive visually represents just a fraction of what exists, that much of cosmic reality lies beyond the limits of our unassisted vision. But even our most advanced multi-wavelength observations remain fundamentally limited by the properties of electromagnetic radiation. Light, regardless of its wavelength, can be blocked by intervening matter. It travels at a finite speed, creating a delay between cosmic events and our observation of them. And it cannot reach us from beyond our cosmic horizon, where the expansion of space outpaces its speed. To move beyond these limitations, we must consider not just alternative wavelengths, but alternative carriers of information, entirely cosmic messengers, beyond light that reveal aspects of the universe invisible to electromagnetic observation. Neutrinos, nearly massless particles produced in enormous numbers by nuclear fusion in stellar cores, pass through matter with minimal interaction. A neutrino can travel through a light year of lead with only a 50% chance of being absorbed or deflected. This ghostly property allows neutrinos to escape from regions opaque to light, bringing us information about otherwise invisible cosmic processes. The detection of neutrinos from the Sunday has confirmed our understanding of nuclear fusion in stellar cores, revealing the reactions occurring in regions we can never directly observe with telescopes. The neutrinos from Supernova 1987A arrived at Earth hours before the first light from the explosion, providing early warning of the stellar cataclysm and information about the initial collapse phase that remained hidden from electromagnetic observation. Future neutrino observatories might detect signals from stars and galaxies throughout the cosmos, including those hidden behind dust clouds or in the earliest stages of collapse before light can escape. Each detection would represent a direct, physical connection to cosmic processes invisible to traditional astronomy, expanding our awareness beyond the limitations of light. Cosmic ray-shy energy particles, primarily protons and atomic nuclei, accelerated to near light speed by various cosmic processes, offer another window into the invisible universe. These particles carry information about energetic events throughout the cosmos, including those in regions hidden from direct telescopic observation. When a high-energy cosmic ray strikes Earth's atmosphere, it creates a cascade of secondary particles that can be detected by observatories on the ground. By studying the energy, composition, and arrival directions of these cosmic rays, astronomers gain insights into processes occurring in distant and hidden regions of space. Though cosmic rays are deflected by magnetic fields in space, making it difficult to trace them back to their precise origins, they nonetheless provide valuable information about the high-energy universe beyond our direct vision. Gravitational waves, ripples in spacetime caused by the acceleration of massive objects, represent perhaps the most revolutionary new channel of cosmic information. Unlike electromagnetic radiation, gravitational waves pass through matter virtually unaffected. They travel at the speed of light, but carry fundamentally different information than photons, revealing the dynamics of mass rather than the properties of charged particles. The first detection of gravitational waves in 2015, from the merger of two black holes about 1.3 billion light-years away, demonstrated the power of this new observational window. Black holes emit no light, making them invisible to traditional telescopes unless they're actively accreting matter. But their mergers produce powerful gravitational waves, allowing us to detect and study these otherwise invisible cosmic events. Future gravitational wave observatories, both on Earth and in space, will detect signals from a variety of massive objects throughout the cosmos, including those in regions obscured to electromagnetic observation. They will reveal the population of black holes, neutron stars, and other compact objects, the dynamics of binary systems, and potentially even echoes from the earliest moments of the universe itself. These alternative cosmic messengers, neutrinos, cosmic rays, gravitational waves extend our awareness beyond the limitations of light, revealing aspects of the universe that would otherwise remain hidden. They allow us to develop a more complete understanding of the cosmos, one that encompasses not just what we can see, but what we can detect through all available channels of information. But even these alternative messengers remain subject to some of the same fundamental limitations as light. They cannot travel faster than light, so they too are constrained by the cosmic horizon created by the expansion of space. They cannot bring us information from before the universe became transparent to them. They cannot reveal the internal structure of black holes or provide direct information about regions beyond our cosmic horizon. To truly transcend these limitations, we must consider not just alternative messengers, but alternative frameworks for understanding the cosmos entirely. We must venture beyond observation itself, beyond the gathering of empirical data, to the realms of theory, inference, and imagination, intellectual tools that allow us to extend our comprehension beyond what we can directly detect. Theoretical physics, particularly in its most abstract and mathematical forms, provides frameworks for understanding aspects of the universe that remain forever hidden from direct observation. Quantum field theory describes the behavior of particles and forces at the smallest scales, including processes that occur too quickly or at too small a scale to be directly observed. General relativity characterizes the large-scale structure of spacetime, including regions beyond our cosmic horizon. String theory and its variants propose unified descriptions of all fundamental forces, potentially explaining the origin and nature of physical law itself. These theoretical frameworks, tested against available observations and refined through logical consistency and mathematical elegance, extend our understanding far beyond what we can directly see or detect. They allow us to model the earliest moments of the universe, the interiors of black holes, the regions beyond our cosmic horizon, and other aspects of reality that remain forever invisible to direct observation. Computer simulations based on these theoretical frameworks further extend our cosmic vision. By modeling the evolution of the universe from its earliest moments to the present day, cosmologists can infer the likely properties of regions beyond our direct observation. By simulating the formation and evolution of stars, galaxies, and larger cosmic structures under various initial conditions, astronomers can test theories against observations and predict what might exist in unseen regions of space. These simulations, increasingly sophisticated as computing power advances, create virtual universes that we can study in detail, varying parameters, to see how different initial conditions or physical laws would affect cosmic evolution. They allow us to explore counterfactual scenarios, alternative cosmic histories, possibilities that may be realized in regions beyond our horizon or in other branches of a potential multiverse. But theory and simulation, powerful as they are, remain constrained by human imagination and cognitive limitations. To move beyond these constraints, to develop truly alternative cosmic perspectives, we might need to consider forms of intelligence fundamentally different from our own, either artificial intelligences of our creation or hypothetical alien intelligences evolved under different conditions and with different perceptual and cognitive apparatus. Artificial intelligence systems designed to process and analyze vast amounts of data across multiple channels might develop insights into cosmic patterns invisible to human perception. Without the evolutionary and cognitive biases that shape human thinking, AIs might recognize correlations, patterns, and possibilities that we overlook. They might integrate information from various observational channels, electromagnetic, gravitational, neutrino, cosmic ray, in ways that reveal previously hidden aspects of cosmic structure and evolution. Already, machine learning algorithms have identified patterns in astronomical data that escaped human notice, discovered new types of cosmic objects, and helped refine theoretical models. As these systems become more sophisticated, they might develop what we could call alternative cosmic perspectives, ways of understanding the universe that differ fundamentally from human comprehension, yet remain valid and informative. Even more speculative are the potential cosmic perspectives of hypothetical alien intelligences. Evolved under different conditions, perhaps with different sensory organs and neural architectures, such beings might perceive and comprehend the cosmos in ways radically unlike our own. They might be sensitive to aspects of reality that remain invisible to us, might process information in patterns we cannot recognize, might develop theories and models that exploit features of the universe we overlooked or misunderstood. While such alien perspectives remain purely hypothetical, considering their possibility reminds us of the contingent nature of our own cosmic vision. The way we perceive and understand the universe is shaped not just by the fundamental physics of reality, but by the specific evolutionary history and cognitive architecture of our species. Our cosmic perspective is not the only possible one, not necessarily the most comprehensive or accurate one, but simply the one that evolved on this particular planet under these particular conditions. This recognition of alternative possibilities, of cosmic perspectives beyond our own, serves not to diminish human understanding but to contextualize it within a larger framework of potential comprehension. It reminds us that the universe is not just what we can see or even what we can theorize, but a reality that exists independent of any particular observer or theoretical framework. The stars we will never see, hidden from our direct observation by various physical limitations, remind us of the partial nature of our cosmic vision. They represent not just specific objects beyond our view, but symbols of all that remains invisible to our particular mode of perception and comprehension. They challenge us to expand our understanding, to develop new channels of observation, new theoretical frameworks, new cognitive tools for grasping the fullness of cosmic reality. Yet even as we acknowledge the limitations of our cosmic perspective, we can appreciate its remarkable extent and depth. From our vantage point on this small planet, we have detected light from galaxies billions of light years distant, measured ripples in space-time from merging black holes, captured ghostly neutrinos from stellar explosions, developed theories that successfully predict cosmic phenomena across scales from subatomic particles to the largest cosmic structures. This achievement, this extension of awareness, far beyond our immediate surroundings, this comprehension of processes and entities vastly larger, smaller, more energetic, and more ancient than our everyday experience, it represents one of humanity's greatest intellectual accomplishments. It demonstrates the power of scientific inquiry, of technological innovation, of theoretical creativity to transcend the apparent limitations of our biological nature. Through these tools, we have developed a cosmic perspective that, while inevitably partial and contingent, nonetheless encompasses far more than our unaided senses could perceive. We have extended our awareness across billions of light years and billions of years, detecting and comprehending phenomena our ancestors could scarcely have imagined. And in this expanded cosmic vision, the stars we will never see take their place alongside those we can directly observe, part of the same interconnected cosmic whole, all subject to the same physical laws, all contributing to the same grand story of cosmic evolution. Though invisible to our telescopes, they remain integral to our understanding of the universe, their existence and properties inferred from theory, simulation, and indirect evidence. Beyond the light, beyond even our current alternative channels of cosmic information, lies a universe richer, more complex, and more interconnected than any single perspective can fully comprehend. It's a universe that speaks to us through multiple messengers, that reveals itself through multiple frameworks of understanding, that exists independent of, but accessible to our ever-expanding awareness. The recognition of alternative cosmic perspectives, of ways of perceiving and comprehending the universe beyond our current capabilities, serves not to discourage exploration, but to inspire it. It reminds us that the cosmic frontiers extend not just outward to distant galaxies, but inward to new modes of observation, new theoretical frameworks, new cognitive tools for grasping the fullness of reality. As we continue our cosmic journey, we might consider not just what more we can see, but how else we might see it. What alternative perspectives, what new channels of information, what different frameworks of understanding might reveal aspects of the universe currently hidden from our awareness. We might develop not just more powerful telescopes, but more varied channels of cosmic information, more diverse theoretical approaches, more sophisticated cognitive tools for integrating and comprehending the data we receive. In this ongoing expansion of cosmic perspective, the stars we will never see serve as reminders of both our limitations and our potential. They symbolize what remains beyond our current vision, while inspiring us to develop new ways of seeing, new modes of understanding, new approaches to the great cosmic mystery that surrounds us. For in the end, the universe is not just what we can see with our eyes or our telescopes, not just what we can detect with our instruments, not just what we can model with our theories, but a reality that exists in its full complexity, regardless of our perception of it. The stars we will never see are as real, as significant, as integral to the cosmic whole as those that grace our night sky. They remind us that the universe is always more than our current understanding, always calling us to expand our vision, always inviting us to explore beyond the boundaries of what we currently know or can conceive. As we gaze up at the night sky, filled with stars visible to our eyes and instruments, we might remember the invisible majority that lies beyond our direct observation, the stars too distant, too obscured, too far in the past or future for their light to reach us. We might consider how our understanding of these unseen stars has evolved through theoretical models, computer simulations, and indirect evidence, how our cosmic perspective has expanded beyond the limitations of direct visual observation to encompass a more comprehensive view of the universe. And we might wonder, what further expansions of perspective await us? What new channels of cosmic information might be discovered? What new theoretical frameworks might be developed? What new cognitive tools might be created to extend our understanding even further beyond the limitations of our current vision? For the cosmos speaks to us not just through light, but through gravity, through particles, through waves in space-time, through patterns and structures across all scales of existence. The stars we will never see, though invisible to our eyes, remain part of our cosmic understanding, integrated into our ever-evolving picture of the universe, as it exists in its totality, seen and unseen, observed and inferred, known and yet to be discovered. They remind us that the cosmos is always more than our current comprehension, always inviting us to look deeper, to listen more carefully, to understand more fully the magnificent reality that surrounds us, encompasses us, and of which we are an integral part. As our cosmic journey draws to a close, we find ourselves once more beneath the vast dome of the night sky, gazing up at stars that have become more than mere points of light. They have become characters in a grand narrative, each with its own storysome visible to us, others forever hidden from our sight, yet all part of the same cosmic tapestry. The night sky above is both a window and a mirror. It shows us the visible universe while reflecting back our quest to understand what lies beyond our vision. Each star we see is a known chapter in the cosmic story. Each unseen star is a chapter we may never read directly, yet whose existence enriches our understanding of the narrative as a whole. When you next look up at the night sky, remember that what you see is just the beginning. For every star that catches your eye, billions more remain hidden behind veils of dust, beyond the reach of light's finite speed, past the horizon of our expanding universe, or lost to time itself. These unseen stars burn in splendid isolation, their light traveling through the void, perhaps never to be seen by any living thing. Think of the light that left distant galaxies billions of years ago, journeying toward us through the expanding cosmos, only to be outpaced by the stretching of space itself. Those photons continue their journey, traveling at the universe's fundamental speed limit, yet falling ever further behind as the space ahead expands faster than they can cross it. They carry information about stars and worlds we will never see, stories we will never hear, messages that will travel eternally without ever reaching a recipient. Consider the stars that lived and died before Earth formed. Their light passed by our location billions of years before our planet existed to receive it. Though gone now, their legacy lives on in the heavy elements they created: the carbon in our cells, the oxygen we breathe, the iron in our blood, the gold and silver we prize. We are, in a very real sense, made from the remnants of stars we will never see, their atomic signatures written into our physical bodies. Imagine the stars being born right now in distant galaxies, their first light just beginning its journey across the void. By the time that light reaches the region where Earth orbits, our Sunday may be a red giant or a white dwarf. Human civilization, if it still exists at all, may have evolved into forms we cannot predict. Those future observers will witness the birth of stars from our era, seeing them not as aged objects, but as they were at their birth, their light preserved by the vacuum of space, despite the billions of years of travel. Picture the stars hidden behind clouds of interstellar dust shining brightly but visible only to instruments that can detect their infrared glow or the radio waves that penetrate the cosmic fog. These obscured stars include some of the most dramatic environments in our galaxy's stellar nurseries where new suns are being born. The chaotic regions around our galaxy's central black hole, the dense cores of star clusters where countless suns orbit in close proximity. Though hidden from our direct view, these regions shape our galaxy through their gravitational influence, their radiation pressure, and the stellar winds and explosions that stir the interstellar medium. Remember the potential stars that never formed, the clouds of gas that were dispersed before gravity could pull them into stellar density, the brown dwarfs that accumulated almost enough mass to ignite nuclear fusion in their cores, but fell just short. These stellar might-have-beens represent cosmic roads not taken, alternative histories that never unfolded, yet their presence as substellar objects still influences the evolution of our galaxy. And think of the stars in galaxies beyond our cosmic horizon, so far away that their light, though traveling since the early universe, will never reach us due to the accelerating expansion of space. These stars exist as surely as those we can see, yet they will remain forever invisible to us, separated by a gulf that not even light can cross. Their stories unfold in parallel to ours, disconnected by physics yet united by their origin in the same cosmic beginning, and their adherence to the same fundamental laws. All these unseen stars, the distant, the obscured, the extinct, the unborn, the unreachable, fill the universe. With light we cannot detect, with stories we cannot hear, with possibilities we can only imagine. They remind us that the cosmos is not just what we can see, but what we can infer, deduce, and understand. Through science, through theory, through the extension of our cosmic imagination beyond the limits of direct observation. The universe we can observe, as vast and complex as it appears, represents just a fraction of what exists. Beyond our cosmic horizon, beyond the reach of our most powerful telescopes, beyond even the theoretical limits of what we can ever directly detect, the cosmos continues filled with stars and galaxies and worlds, and perhaps even civilizations whose existence we can infer, but whose specifics will remain forever hidden from us. Yet this invisible majority of the universe is not separate from us. We are connected to it through gravity, through the elements forged in distant stellar furnaces, through the fundamental unity of physical law that governs all regions of space and time. The unseen stars, though invisible to our direct observation, remain part of our cosmic context, shaping the universe we inhabit and helping to determine its future evolution. As we conclude our journey through the stars we will never see, let us carry forward this expanded cosmic perspective. Let us remember that reality extends far beyond what we can directly observe, that existence does not depend on observation, that the universe is even grander, more complex, and more mysterious than what meets our eyes or our telescopes. The stars we will never see still shine, still burn, still dance in the dark, and though their light will never find our eyes, we are part of their story. Our existence has been shaped by unseen stars long extinct. Our future will be influenced by unseen stars yet unborn. Our present is connected to unseen stars in distant galaxies through the invisible threads of physics that bind the entire cosmos into a unified whole. Sleep now beneath a sky filled with the unseen, and know that they are there, the stars behind dust clouds, the stars beyond our cosmic horizon, the stars that died before we were born, the stars whose light is still en route, the stars that will form long after we're gone. Know that the visible universe, as vast as it appears, is just the beginning. Beyond what we can see lies a cosmic ocean of possibilities, invisible to our eyes, but accessible to our understanding, mysterious yet governed by the same physical laws that shape our observable corner of creation. The stars we will never see remind us both of our limitations and our potential boundaries of our direct observation, and the power of our scientific imagination to transcend those boundaries. They invite us to look deeper, to think more expansively, to develop new ways of understanding the cosmos in all its seen and unseen glory. For in the end, The universe is not just what we can see, but what is. Not just what we can directly observe, but what we can comprehend through all the tools of science, theory, and imagination. The stars we will never see are as real, as important, as worthy of our attention and understanding as those that shine visibly in our night sky. They are part of the complete cosmic story, a story we can never read in full, yet one whose broad outlines we can discern through the remarkable journey of scientific discovery that has brought us to our current understanding of the cosmos. Rest now in this knowledge, in this expanded awareness, in this cosmic perspective that encompasses both the seen and the unseen. The universe is larger, older, more complex, and more interconnected than we can fully comprehend. And that is its greatest wonder, its most profound mystery, its most beautiful truth.